The following message is best viewed on an oscilloscope.
Okay, so Alex, it's now completely yours.
Okay. Hello to everybody. I am glad to welcome you at the session of Upgrade and Performance Detector, which is devoted to the colorimetry and mirrors. So since our schedule is quite tough, we have to follow schedule. So please try to be in time, and during the talks, please mute your microphones. And after finishing, you can ask question, raising a hand or writing in the chat. Okay, so let's start from the first talk. Dario will talk about precision colorimetry at high luminosity, the CMS electromagnetic colorimeter from the LHC run 2 to the high luminosity LHC. Please go ahead.
Thank you. Good afternoon, everybody. I'm glad to be here to show you the CMS electromagnetic colorimeter, the upgrade from the LHC Run 2 to the iLumi LHC. The electromagnetic colorimeter of CMS is characterized by a high granularity. It's almost 76,000 crystals of lead tungsten. These allow the detector to have a fast decay scintillation light with a short radiation length to gather a small Mollier radius. And the crystals are read by avalanche photodiodes, the APDs. And of course, the detector is fundamental for the particle identification in CMS to detect the electron and gammas, but also jet. And it's good, the photon mass resolution of about 1% has a crucial role for the discovery, for example, of the Higgs boson, but in many other CMS analyses, of course. In the Run 2 conditions, we had to fight against two different enemies. One was the higher integrated luminosity with respect to Run 1. This means a larger radiation dose that increase the loss of light of the crystals. Basically, it's a transparency degradation of the crystals and the radiation-induced aging of photodetectors and of the detector readout in total. The other enemies is the pile-up, because with respect to Run 1, in Run 2 and in Run 3, we have a higher bunch intensity and a 25 nanosecond bunch spacing. This has an impact on the pulsar construction. You can see in the plot in the slide on the left, what does it mean, the radiation dose that decrease the transparency of the crystals. Basically, we have that at the end of the Run 2, the barrel has lost 13% of the transparency, while for the end cap, it's even worse. And we have to monitor each channel with a dedicated laser system and perform every 40 minutes a check, and then the correction will be provided every 48 hours. This regular calibration allows to maintain an excellent energy resolution and a good stability over the time, as you can see in the plot on the right. But we have also to implement a multi-fit algorithm considering the out-of-time pulse effect to mitigate the pile-up at the construction level. And we will not speak about this. There is a poster dedicated by Dimitri. And so I can go directly for the high Lumi, which is the challenge. basically we want to maintain the same performances even in the phase 2, when the pileup will be 5, even 7 times larger. Just to give you an example, at the luminosity of 5 times 10 to the 34 centimeters square per second, we will collect almost 1 inverse femtobar every 5.5 hours. This implies to have a higher trigger rate, of course, and a higher bandwidth to be sustained. Of course, a higher radiation that implies a higher noise, and a higher anomalous high energy signals that we call spikes. Those spikes are basically signals of hadrons that interact directly with the APD instead of the crystals. And we want to reject these spikes, and we want to change the electronics in order to reject these spikes. In fact, what we can do to sustain the phase 2 luminosity is the substitution of the end cap part of ICHEP with a new high granularity calorimeter. And for the barrel, we have to reduce the temperature from 18 to 9 Celsius degrees to mitigate the APD dark current. And we have to upgrade the ICHEP barrel electronics in order to have precise timing, the spike rejection, and the full detector readout at level 1. The precise timing in phase 2 is quite important, it's quite peculiar for a calorimeter, because when you run at 140 or 200 pileup, the vertex reconstruction efficiency is reduced to 30%, for example, for the X in gamma gamma. If you want to constrain the vertex localization in 1 centimeter, you have to use a precise timing of about 30 picoseconds. In this case, you will have a 10% improvement in the fiducial translation sensitivity and the X gamma gamma resolution. Regarding the X gamma gamma resolution, you can check the plot on the right. You can see that the green curve is the precision without any timing applied, while if you have a precise timing of 30 picoseconds, you get more 10% more better precision. While if you add the timing layer, which is presented by Nalu on Tuesday, you can basically go back to the run 2 situation. So the message is that the new readout chain is specified to deliver the desired time resolution of 30 picoseconds for energy greater than 50 GeV. In general, we change the preamplifier of the electronics from a charge-sensitive amplifier to a transimpedance amplifier with different gain values in order to use less number of bits. In fact, then we have to use analog to digital converter of 12 bits. And we move from a frequency of 40 megasample to 160 megasamples per second in order to obtain the 30 picosecond resolution, timing resolution that we want. And we have to compress the data. In fact, before, data were sent out of the detector in pipeline, but before in the front end, we were doing the trigger primitive generation in a tower of 5x5 crystals, while now we will send data of detector using the LPGBT data links with the trigger data granularity of the crystal. So we are not using any more the towers, but we have a full readout at the trigger level for the detector. This means that if you try to deliver the entire, all the channels with 13-bit words, the channel bandwidth is 2.08 gigabit per second, while the LPGBT rate, it's 1.28 gigabit per second. So you have to basically reduce over a factor 2 the bandwidth. And how we do it is with a very simplified Huffman code. Basically, we usually send data with 6 bits that we call baseline. So in 6 bits, you can store basically 2.4 GeV. And usually you have less than 2.4 GeV. So 6 bits are enough to describe the energy. In fact, the probability to have more than 2.4 GeV in a single crystal per event, it depends on it, of course, but you can see that it's at the level of 10 to the minus 4. While for a signal with higher energy, you send 13 bits, 12 of the ADC plus 1 that tells you if you are using gain 10 or gain 1. So a signal multiplied by a factor 10 or a signal multiplied by a factor 1. We test the CATIA, so the transimpedance amplifier, in a test beam connected with a 160 megahertz commercial ADC, so not with the final ADC and transmission unit that we will have, but with an electron beam in a range of 25 to 250 GeV, and the temperature currently used in ICHEP. And we find that even with a commercial ADC, we are good enough to match with the energy resolution of the actual electronics, and the time resolution match the targets of 30 picoseconds. Moreover, the new transimpedance amplifier is able to well separate the signal from the spike with respect from the electromagnetic shower in the crystal. As you can see in run 2, the two signals are basically the same, while for the phase 2, you can see that we are able to separate them already at the trigger level and can reject them. Now we are doing several tests to characterize the full electronics chain, like the radiation hardness, which is of course fundamental for high Lumi, the characterization of the transimpedance amplifier with the gain, with the noise, and also the characterization of the light DTU ADC, like the effective number of bits, the INL, DNL. And finally, we are now testing for the first time the connection between the CATIA and the light DTU. I've just put a couple of pictures of the test, radiation hardness test that we did in various facilities like Padova, like Pavia, like Louvain, etc. So to conclude, the transition from the round 2 condition to the high luminosity for the CMS calorimeter has been presented. In round 2, the increased pile-up and radiation required to constantly monitor and calibrate the detector, and the system maintained indeed an excellent energy resolution together with a good stability over the time. Nevertheless, if you want to go to phase 2, you have to do some intervention, like the substitution of the NCAP with a high granularity calorimeter. You have to reduce the temperature in the barrel, and you have to build a brand new electronics for the barrel. This will provide a time resolution of about 30 picoseconds to mitigate the pile-up effect, and will provide a new shaping in order to reject the spikes already at the readout level. And it will allow to read each single channel already at the trigger level, providing a full detector readout for the trigger. Preliminary results from the test bench have shown promising results with only CATIA and a commercial ADC sample at 160 megahertz. While now we are doing some tests with the IDTU block, and that's it. Thank you for the attention.
Okay, thank you. Questions to Dario?
Maybe I would like to ask, if I can, I would like to ask what are the expected fluencies for the high luminosity, during the high luminosity LHC? I mean, like total fluencies for the full high lumi life.
The exact number I don't remember. It's written in the TDR. Sorry, I will send you.
Okay, no problem. And maybe the second question: what parts of the calorimeter will be most affected by these fluencies, like detection parts or electronics?
Well, the electronics, of course, has to fight against the radiation. And while for the crystal is okay, once you know how to calibrate the crystal, you can correct it. While for the electronics, you have to make it working even at a higher fluency. So that's the point.
Okay, thanks.
Okay, I don't see other request for question. May I ask a short question? During test beam, you carry out measurements at 18 degrees. Did you perform measurements at 9 degrees?
Not yet. No, this is something that we have to do. Unfortunately, we have a bit stop due to the COVID, and there are many tests that we want to do that are still pending.
Okay. Okay. Thank you again. So let's move to next presentation. Pavel.
Hello, good morning or good afternoon. I would like to say a few words about Atlas liquid argon calorimeter commissioning and preparations for the run 3. Short outline of my talk, I will say a few words about the calorimeter and the preparation for the next run, and will describe in more details the phase 1 upgrades which are currently ongoing and which is most of the work done during the LS2. Liquid argon calorimeter for Atlas is using three geometries, let's say. In the central barrel, it uses accordion geometry. In the hadronic end cap, it is the parallel plate geometry. And in the forward detector, it's the very new design of the cylindrical electrodes parallel to the beam. The calorimeter is highly granular. We have in total nearly 200,000 channels and covers have the full coverage up to eta 4.9. So it's very useful for identification of the particles, for measuring the jets, and so. The calorimeter signals are amplified outside the cryostat in the so-called front-end boards, which has 128 channels each. And on the board, the signal is split into the three gains in order to cover the full dynamic range of the detector. And then the signal is sampled and stored in the analog pipelines. And only in the current readout, once the level 1 accept signal comes, then the proper gain is selected and transmitted to the backend. In addition, we are sending the analog signals to the level 1 trigger system. This is done before last stage of the integration. And we have nearly everywhere around 2 millimeter gaps in the liquid argon, and with 2 kilovolt nominal high voltage, our drift time is around 450 nanoseconds. So now, why we are thinking about some upgrades, we could not change the detector itself, of course, that's too costly and too much time. But with the increasing luminosity, which we expect in the run 3, around mu 80, there will be quite challenging to select the right event, because the Atlas plans to stay with the same level 1 rate as during the run 2, around 100 kilohertz, out of which the 20 kilohertz should be devoted to electrons and gammas, which are the primary particles identified by the liquid argon calorimeter. These luminosities were achieved during the run 2 already, but only for the short time. And for the run 3, we expect to have such conditions for most of the beam time. So in order to achieve the goal to keep the trigger efficiency S in the run 2, and to stay within this 20 kilohertz rate without some important acceptance loss, we need to do something without triggering. And because we could not change the detector, as I said, but we have enough granularity in the detector itself, we have prepared the upgrade, which by using this higher granularity in the trigger, will be able to stay with the expected rates without raising the ET thresholds. And even this higher granularity allows to use some shower shape variables to better distinguish, I mean, the electrons and the jets already in the trigger, and also to use some rejection criteria similar to offline algorithm, which will better reject the QCD background jets. So this upgrade in the trigger consists basically from the new digital trigger boards, which directly in the front-end crate are taking the existing trigger signal from the front-end board, but with much higher granularity. And this will allow to achieve the goals which I have now just described. In order to have this board working, we need many more signals coming from the front-end board to this new trigger digitizer, as well as to exchange this layer sum board on the fab, which are collecting and summing the signals from the few cells to form the analog trigger signal. We need to do this now with much higher granularity. So this was the proposal, and we are now intensively working during the LS2 to implementing. Basically, for this, we needed to reinstall all our crates with electronics on the cryostat, exchange the base planes. On the top right plot, you see the picture of the one new base plane, which needs now to route 10 times more signals than before. They are all produced, and more than 80% of them are installed, as well as these new layer sum boards are produced. And we are working already for more than a year to refurbish these front-end boards, which has many steps to do the thing. It needs unmount the cooling plates, exchange the thing, put back, test the leak, test all the parameters of the fab. But I mean, with the external contractor, we are happy with the work which is ongoing in the it was ongoing in the rate more than 50 fabs per week. And afterwards, the fabs are reinstalled back to the detector because we don't have enough space in the lab to keep them all. So now how this new board looks like, or what was needed to have the expected performance, is not only to develop our custom ADC, because we required very low power consumption. We were simply adding the boards to the front-end crate, which has already quite some power, and we were not able to increase it too much. Another part which was very interesting for development was the optical transceiver, because there is no commercial modules, or were not available at the time where we were planning this. And we had less than 6 millimeters space on the board available, and the typical height of the optical transceiver is around 14 millimeters. So we have developed our transceivers, and they are multiplexing the ADC channels from the board, and use the 5 gigabit links, and there is 20 such modules, 2 channels modules per digitizer board. All this work is already going on, and then the data should be passed to the digital processing system, which some characteristics you see here. And this system needs to reconstruct the ET time and transmit all this to the level 1 trigger system. The whole thing needs to work as it is triggered with a very strict latency limit for the computations, around 5 or 6 bunch crossing. And we are currently investigating different filtering options to get the maximum performance. So the status of the work, one can see on such diagram, which shows 4 phases of our colorimeters, and with the different coloring code, the status of the individual crates. Basically, the barrel A site is now fully completed with all boards back, everything cabled and already tested. In the end cap A and barrel C, we have mostly front and boards back. Some parts are also cabled, but we are missing there the digitizer boards and cabling still. And the refurbishment work of the fabs is still ongoing on the end cap C side currently. So we were able to keep our system running despite the COVID lockout, and even some people were able to bring their test setup to home. So the firmware and software development was not interrupted, and we resumed the installation in Atlas Cavern in mid-May. So most of the hardware components are either produced or the production should be finished after the summer. Another very tedious task was to route many optical fibers in the already full Atlas cable trays and bring the signals to the counting room, but it was achieved at the end, and you see now in the photos some examples of the backend installation in the counting room. And as well as for these front-end boards, we have all the hardware already produced, and we are starting now the integration tests and commissioning on the real system. Recently also the Felix servers, which are the common CERN product for the control, monitoring and providing a DAC, has started, and the lower photo here shows the connection of all LTDBs from the barrel A to the Felix server, so we can now control and read out the big chunk of our detector already. And in recent milestone week in Atlas data taking, we achieved the goal to run the full chain of the phase 1 hardware up to deliver the data to the Atlas centrally recorded events. So we could be sure that the PCs which we are installing now and we are commissioning are working fine. Of course, the preparations for the run 3 are not only the phase 1 trigger upgrade, but we need to refurbish and improve all our infrastructure. And what it concerns offline software, which need to be migrated to the multi-threaded environment, because these high pile-up events in the run 3 will need too many memory for the reconstruction. So this was already done for our detector specific code, and it's extensively testing now. The similar we need to do with all the data quality infrastructure, monitoring and similar tools, which help us to keep a very high quality of our data. So that's also basically migration to the multi-threaded environment and the testing currently. We also need to...
You have 1 minute left.
Yes, I will one slide more. To migrate the online software, where the main task now is the inclusion of all the packages which are needed to work with the newly built phase 1 trigger elements. And similarly for the detector and control systems, which are now integrating all the new delivered hardware. So in conclusion, our liquid argon calorimeter achieved excellent performance during the run 2, and in order to keep it also in the harsher environment in the run 3, we are refurbishing all infrastructure software-wise and workflow and data taking wise, and as well we are successfully installing and commissioning the phase 1 upgrade, creating a digital trigger which should allow us to keep our performance. And despite no major delays were developed during the lockdown, so we should be ready to, in time and ready tested for the LHC restart. Thank you.
Okay, thank you. Questions to Pavel? So let me ask some question about after your modification. Do you expect some improvement of performance, or it just will be the same?
No, I mean it will not improve the reconstruction itself. It will only improve the triggering efficiency. I mean, or better say, our trigger will stay equally efficient also in higher pileup environment, and it should be also will be also used in the after phase 2 upgrade in the high Lumi LHC, a so-called level 0 trigger for the new triggering full digital trigger system. So the performance of the detector itself, we expect to stay the same.
Okay. I don't see other questions. So thanks.
Thank you,
Pavel. So let's move to next presentation, performance of Atlas type colorimeter for Sergey.
Hello, can you hear me?
Yes, we can hear you, but we cannot see your slides.
Yes, it seems to be a problem. I cannot share them. Is it possible to share somehow?
Yes, give me a second. I will try to download them and share them. Just a second.
Okay, many thanks. Okay, many thanks.
Can you see them?
Not right now, but okay, I see them right now. Is it possible to make them?
Give me a second. It's
okay.
a bit mess. Okay, just a second, please.
Control and L.
I think you can press F5.
Yeah. F5 and now.
I think it's Control and L.
Okay, let's try this.
Okay, now it's much better. Many thanks. So I would like to present the status about performance of the Atlas tile colorimeter. Next slide, please. The tile colorimeter is central hadronic colorimeter in the Atlas detector, which measures hadrons, jets, missing transverse energy, and provides input to level 1 colorimeter trigger and assist in muon identification. As one can see from the top plot, it consists of 3 barrels, 1 long barrel and 2 extended barrels, and each of them is divided into 64 modules. It is sample colorimeter with iron plates as passive material and plastic scintillating tiles as active medium. Each tile is read out by 2 PMT from each edge, as one can see on the bottom left plot, via wavelength shifting fibers. And there are about 10,000 readout channels, which will give about 5,000 cells, which are formed by grouping fibers into bunch and connecting it to the same PMT. The cell layout one can see on the bottom right plot for 1/2 of long barrel module and 1 extended barrel module. One can see here 3 layers in depth like A, B, C, and D, and 1 layer of E cells. The aim for jet energy resolution is given by formula at the bottom of the slide. Next slide, please. On this slide, one can see signal processing and calibration tile colorimeter. So signal from PMT is shaped, amplified into gains, low and high gains with the ratio of 64:1 and digitized each 25 nanoseconds. Upon receiving trigger decision, amplitude and time are reconstructed from 7 consecutive measurements, like it is presented by formula in red color, in blue color, with so-called optimal filtering algorithm. The energy is evaluated from amplitude using calibration coefficients, like it is shown by formula in red color. The first calibration factor is provided by charge injection system, which monitors electronic chain stability and linearity. The second one is actually electromagnetic scale, which was measured and fixed in special test bin campaigns. And third one is provided by cesium calibration system, which monitors all optic components like tiles, fibers, and PMTs. And the last one is provided by laser calibration system, which monitors PMT stability. As one can see from the bottom plot, the path of different calibration system partially overlaps, and that allows cross-checking of different calibration systems. Next slide, please. Charge injection calibration system injects a signal of known charge and measures the electronic response. It is spanning full ADC range from 0 to 800 picocoulomb. In such a way, it provides the possibility to probe 2 gains for each channel and allows to extract the conversion factor from ADC count to picocoulomb. And one can see from the right plot distribution of this calibration factor for low gain from whole tile colorimeter. Calibration is performed about weekly during special calibration runs. Precision is about 0.7% and time stability is 0.03%, as one can see from the left plot, whereas it shows time evolution of calibration factors for whole run 2 period. It is also used to calibrate analog level 1 colorimeter trigger. Next slide, please. The cesium calibration uses a movable cesium radioactive source, which passes through the colorimeter body. It is done 2 or 3 times per year in run 2 in special cesium runs. It uses independent integrator readout, which during source moment, which integrates the signal in time window about 10 milliseconds. Deviation of the cell response in time is caused by PMT gain variation and scintillator degradation, and is converted in additional calibration factor. On the right plot, one can see maximum drift as it is seen by cesium systems over whole run-to period for different cell types as function of eta. And the left plot, one can see the time evolution of these calibration factors. Not calibration factors, but down drift. In both cases, they are corrected for cesium decay. As one can see, maximum drift is in layer A, which is the closest to the collision point. Precision in typical cell is about 0.3%, and that allows to adjust PMT gain by changing high voltage to restore colorimeter response uniformity. Next slide, please. Laser calibration system sent a controlled amount of light into each PMT. It is performed about weekly during special calibration runs and in empty bunches during collisions to monitor and calibrate timing. It measures the drift seen in PMT with respect to the last cesium scan. And this drift is converted into additional calibration factor. And time evolution of this average PMT drift, one can see on the right plot over whole run-to period. And for different cell types, one can see on the left plot. Precision is better than 0.5%. And maximum drift is observed in A and E cells, which are the cells with highest energy deposits. Next slide, please. Minimum bias systems measures the response to minimum bias events. It shares the same readout with cesium systems, but integrates the signal during data taking. It also monitors the full optical chain and also calibrate E cells and minimum bias trigger scintillators because cesium calibration system are not available for these cells. On the left plot, one can see the typical signal for different cell types as a function of eta. And on the right plot, one can see that measured signals depends on the instantaneous luminosity linearly. And that provides an additional way to measure and monitor the instantaneous luminosity in Atlas. Next slide, please. Comparing different calibration systems allows to get additional information because cesium and minimum bias systems see PMT gain drift and scintillator aging, while in the same time, the laser system only monitors PMT gain drift. And the differences between laser and minimum bias measurements can be interpreted as scintillator aging due to irradiation. And one can clearly see this effect on the bottom plots, the left one from 2016 and the right one from 2017. Next slide, please. Next slide, please. Okay, thank you. Time calibration is very important for cell energy reconstruction. It sets the phase so that a particle traveling from the interaction point at the speed of light gives the signal with measured time equal to 0. Time calibration is calculated using jets and monitored with laser. As one can see from the right plot, the reconstructed mean cell time over whole run-to period is very good. I mean, the stability is very good, and the resolution is better than 1 nanosecond for cells with energy greater than 4 GeV, as one can see this from the right plot. Next slide, please. Total noise per cell in colorimeter comes from two sources. The first one is electronic noise, which is measured regularly in special runs without signal in detector. And the second one comes from multiple interactions in the same or neighboring events and called pileup noise. As one can see from the right plot, electronic noise is below 20 MeV for most of the colorimeter cells. And total noise is increasing with pileup, as one can see from the right plot. the largest noise in the region with highest exposure, A and E cells. Next slide, please. Monitoring of data quality includes identifying and masking problematic channels, monitoring data corruption, other hardware issues, correcting miscalibration and timing. The identified issues are fixed during maintenance campaigns, and that allows good recovery of the system, as one can see from the right plot. Overall data quality efficiency is about 99.7% during run 2. And on the right plot, one can see distribution of masked cells at the end of run 2 period. The red line corresponds to switched off module due to cooling problem. Next slide, please. The ratio of calorimeter energy at electromagnetic scale to track momentum for isolated charge hadrons is used to probe hadronic response. It is measured in minimum bias events. And as one can see from the left plot, the average E over P is 0.67. And it is expected to be below unity due to the non-compensating nature of the sampling calorimeter. And as one can see from the right plot, data and Monte Carlo simulation do agree well within 5%. Next slide, please.
Okay, I'm sorry, we have 1 minute left.
Okay, thank you. Muons from cosmic rays are used to study in situ the electromagnetic scale and the calorimeter cell intercalibration. Cell response is estimated as energy deposited by the muon per length of the track path. As one can see from the right plot, the distribution in phi is very good. And as one can see from the right plot, response non-uniformity in it is below 5%. Next slide, please. And that is just conclusion. Tau calorimeter is an important part of Atlas detector, which measures hadrons, jets, and missing pronounce energy. A set of calibration system is used to monitor and calibrate the signal at each stage. Intercalibration and uniformity are monitored with isolated charge hadrons and high momentum cosmic muons. The stability of absolute energy scale at the cell level is better than 1% during run 2, and the overall data quality efficiency is 99.7% in run 2. That's it from my side. Thank you.
Okay, thank you. Question to Sergey. Okay, I don't see any hands. So may I ask, you showed that according to your CSI, cesium calibration, you have degradation of light output. And do you have some recovery during shutdown?
I don't. Actually, we have recovery only in PMT gain variation, not in the scintillator degradation. And since it by cesium it see both, probably something can be seen as a recovery, but
okay. So for PMT, you observed some recovery of performance?
Yes, one can see on the, I think, comparing different calibration systems on this plot. Okay, probably even on this one can see that during non-collision period, we see PMT updrift.
Mm-hmm. Okay, other questions? Okay, so thanks for your presentations. Let's move to the next presentation. It's presentation performance of Atlas RPC detector and L1 million barrel trigger at square root of S 13 GeV, Kunlin Han. Please go ahead.
Yes, can you see my slides?
Yes.
Okay, so let's start. Hello, everyone. My name is Kunlin Han, and my talk is performance of Atlas RPC detector and level 1 muon barrel trigger at central mass of 13 TeV. So page 2 is the introduction. So in the Atlas experiment, the muon is an important signature, and its efficient selection is crucial to a lot of physics program. The right plot is even display of the ZH candidate in 2 electron and 2 muon final state. The 2 right tracks represent the muons. In order to select the events containing muons, the level 1 muon barrel trigger system is using resistive plate chambers, which is placed in 3 concentric double layers shown in the left figures. The muon candidates are selected using 6 PT thresholds, while the minimum one is 4 GeV. Page 3 is a brief introduction to Atlas resistive plate chambers. In the detectors, RPCs cover a huge number of amount of area, around 4,000 square meters. In each RPC chambers, it consists of 2 detect layers, each with eta and phi readed panels. The bottom figures is a schematic of Atlas RPC single layers. From these figures, you see that the 2 parallel resistive plates are separated by 2 millimeters, and the readout system has orthogonal eta and phi strips. And in the gas volumes, RPC use a mixture of 3 gas, and it operates in a safe avalanche mode. The intrinsic resolution of RPC detector is around 1 nanosecond to have a faster response. So in the following slides, I will present the RPC performance results obtained from the 2018 data. They use the probe muon from Z boson productions to avoid potential bias from the trigger. So page 5 is the first result for RPC cluster height multiplicity and cluster size. So the left plot is showing the RPC cluster height multiplicity distributions averaged over all RPC modules. From the first bins, you see a fraction of 60 to 70% muons produce cluster with single hits. And the different construction between eta and phi panels will cause small differences, which is observed from this mean value between eta and phi panels. And then the average cluster size values are calculated for each modules and presented in the right side for the eta and phi view. Next page is for the RPC detector efficiency. This efficiency is defined as a ratio of number of muons selected hits over all probe muons. The selection is for the timing window and also the position cut from the expected muon impact point. In addition, the gap efficiency is also measured, including eta and phi strips. So the left plot shows the individual detector and the gas gap efficiency for one run. Most of gas gap have very high efficiency, around 95%. The electronic efficiency leads to lower average values for the eta and phi panel efficiency. Failing all 2018 runs, it results as a functional time, so the good stability is observed on the right side. Page 7, it's the RPC total time resolution measurement. So the diagrams in the top part, it shows the procedures in this measurement. The H time differences computed by the H, which matched with the same muon track in 2 detect layers for eta of either eta or phi views. Then a Gaussian function fit is applied to extract the width of distributions. The left plot is an example fit for 1 eta strip pairs. And so we summarize the Gaussian width values for the entire RPC system and shown in the right side. After dividing the square root of 2, the total time resolution is around 1.5 nanosecond. And from this mean value, the differences come from the different cluster size composition between eta and phi panels. The next page is the intrinsic resolution of BC detector. The total time resolution includes two components. One is intrinsic detector resolution, and the other is from the readout system. The diagram shows the procedure for the electronic resolutions measurement. The slightly different from the total one, so the time difference is using eta and phi heats in the same gas volume, which observes the same avalanche. The intrinsic part is cancelled and the left plot is the weighted average values distribution for the electronic component for layer 0 and layer 1, also the combined cases. Given the comparable behaviors, we choose the combined result to extract the intrinsic component shown in the right in the right side. And after dividing the square root of 2, the intrinsic resolution is around 1 nanosecond. Okay, so then I was talking about this RPC background counting rate measurement, which is dominated by the secondary particles. The background hit was selected in the time window preceding triggered bunch crossing, and the normalized counting rate was calculated and plotted as a function of instantaneous luminosity on the left side. Different colors represent panels at 3 different radius. For all cases, the linear dependency is observed, and the right plot shows the differential counting rate at a given luminosity for one RPC layer. The background counting rate changes with particle flux at the different eta and radial positions. Page 10 is the RPC current measurement versus the luminosity for several modules. So in the left plot, it shows the RPC current density for modules at different eta positions of 1, 3, and 6. Each point represents one RPC panels. And in the right plot, it shows the result for different RPC size and the radial modules. So similar to the background counting rate results, the current scale linearly to luminosity and affected by the particle flux. And in the right plots, there are some differences between the small and the large sector. It is due to the magnetic coil shielding, and the radius is slightly different. Combining this background counting rates and current results, the effective avalanche charge is estimated by their ratios. This parameter is also a key to the performance. It depends on the electrical field and the gas mixture. The distribution of the average avalanche charge is shown on the left side, and the mean values of 30.4 picocoulomb is in good agreement with the previous measurement. The right plot shows the avalanche charge as a function of eta and phi position. The variations is between among different positions is due to the high voltage and front-end threshold settings. So the second part is a level 1 muon battery trigger performance. So page 13. So the good trigger timing performance require accurate timing calibrations of the RPC hits, which is made in step of 3.125 nanosecond. In one run of data 2015, in the left plot, showing the left plots, about 99.7% of muon candidates are associated to the correct bunch crossings. And in the 2018, the fractions was around 99.6% on the right side, and remained stable during the data taking. Some of the runs have lower values is due to this lost trigger tower. And so page 13 is the trigger efficiency results to detect the muon is measured as a function of several parameters. So then the left plot is showing, the left plot shows the trigger efficiency as a function of offline muon PT for 6 PT thresholds. And so the efficiency is limited by the geometric acceptance and gives stable plateau values above 20 GV. From the right plots, as function of the efficiency as function of the time, the efficiency to detect muon is 76% for low PD thresholds and smaller for high PD ones due to additional requirements. Here is the summary. Again, the efficient muon selection is very important to Atlas program. And many studies have been done to monitor RPC performance during the year. And so Atlas RPCs have been working with excellent performance since completion of the system in 2008. Okay, thank you.
Okay, thank you. Questions to Kunling?
Maybe I would like to ask if there is some plan of the upgrade of these chambers for high luminosity LHC.
Yes, there's two parts. Once the new RPC chambers will be installed, like in the innermost stations, and the other is since for the high luminosity RPCs, it will justify a bit for the high voltage thresholds in order to get a safe performance for the current RPCs.
Okay, thank you.
Okay, one more questions. You showed the dependency of background on luminosity. Do you have dependence of other characteristics? For example, time resolution, is it changing with increasing of background?
No, I don't think. I think we have done that part.
Okay, so you didn't check, or you don't expect, or?
We do not expect a large difference from this current result, actually.
Okay, thank you. Other questions? Okay, thank you.
Thank you.
So let's move to other presentation. Track-based muon system alignment of the CMS detector, Hong-Young Kim.
Yes, can you see my slide?
Yes.
Yeah, so today I will present about the track-based muon system alignment of the CMS detector. So page 2 shows outline. So I will introduce the CMS muon system for alignment and explain the track-based muon alignment method. Then I will show you the physics validation result, and then run through commissioning and summary will be there. So page 3 shows the CMS muon system for alignment. In the battle region, there are DTs. The eta range is up to 1.2, and DT have 5 fields, and each field, the DT is arranged in the pull station. And the pull in chambers in the pull station can only measure the pi direction of the track. And at the handicap region, there is the CSC, the eta region 0.9 to 2.4. And each handicap has a pull station, and the station CSC arranges the rings, and it has up to 3. Page 4 shows the track-based muon alignment method. So this track-based muon alignment method calculates muon residue. So this figure explains that. So we calculate the muon propagation track from the inner track or track to muon system, and there is the 2 hits. One is the reconstructed position, and other one is the predicted position. So if there are the misalignment, that means shift, there will be the muon residue. So this TBMA technique is proven to be efficient, robust, and stable in run 1, run 2, and we consider all possible systematic uncertainties, and then we improved that. And muon system alignment is very important for the muon reconstruction. And this TBMA has a good accuracy order of 100 micrometer. So tomorrow there is the tracker alignment of the CMS detectors. If you have interesting, please attend that. It will cover the details of the CMS inner tracker alignment. So page 5 shows alignment input. So we selected the global muon, the PT range is 30 GB to 200 GB. So minimum PT selection, we to ensure the less scattering, and higher PT 200 GB to ensure the less showering. And we also selected only good quality muon track, so it required at least 10 hits in the inner tracker. And we required NS2 muon chamber matched with the muon, and then we also selected the muon track by chi-square and impact parameter TFY. Here, this figure explains the PDShare selection criteria. So the muon can scattering before the muon chamber, then it makes a smearing. So this case is fine. Any direction inside the chamber, then it just make a larger muon residual distribution. But in this case, the one direction can be outside the chamber and then make some bias, geometrical bias. So to remove this bias, we are using the PDShare selection. Page 6 explains the muon chamber degree of freedom. So this figure shows the DT and CSC, they are local alignment parameters, X, Y, G, and the rotation of X, Y, G direction. So the TBMA, the effectively minimize the residual with these 6 parameters. So for GT, there is residual X and Y, and CSC, there is the residual R pi instead of X. And local X and R pi are in the global coordinate, they are pi direction, and it is the most sensitive direction in the PT resolution. Page 7 shows the accuracy plot. These 2 plots shows the interrupted luminosity and the chamber position RMS. So after 2 inverse pentaband, the RMS distribution getting the saturation. So we recommend NS2 inverse pentaband for this muon alignment. And the accuracy depends on the detector position and type. So you can see difference the field number in station 1 and 4. Page 8 summarizes the run to performance. So during the run to the muon alignment, try to solve the weak mode problem, and also we try to qualify the precision order of 100 micrometer for linear DOF and 0.1 milliradian for the angular DOF. And last year we performed the run to legacy alignment. We did the update and improved the tracker legacy geometry, and we made some detailed interval. So before we have only 1 alignment per year, but now we have 3 alignments per year. And we can also perform with higher integrated luminosity. And the CSC, every year, the end cap was opened. So we need some special the alignment for the CSC. I will explain it details later. So after alignment, we need to check the performance with the physics validation. So I will show the legacy geometry result, the data collected at the beginning of 16, 17, 18 PP collision with a single muon trigger. And for the physics validation, we are using only global muon, which is the conscious track reconstructed independently in a tracker and the muon system. So we selected muon, global muon by inner tracker, eta, and PT, and we calculate the dimuon invariant mass with 2 mass, method, the two global muon or global muon and standalone muon. And we calculated the muon PT resolution by the standalone muon PT and global muon PT. So when we are using the standalone muon part, it is very sensitive to muon alignment result. So this flow shows the invariant dimuon invariant mass and the mass width. So red dot and green dot both want 17 data, same one, but the red dot reconstructed with the 16 geometry. So at the high region, the mass and the mass width was changed due to long geometry. So because we opened the end cap, so it changed only high region. And page 10 explains the CSH alignment. So these two plots showed the R pi residue by the global pi position. So before alignment, it shows the sinusoidal trend because the entire end cap was shifted. After that, the residue became flat. So also this effect to trigger also. So we did some two special alignment, two steps alignment. First step, we shifted the entire disk and then we aligned the individual chamber. So finally, we can get the displacement from initial geometry. So the third flow shows the step 1 plus step 2 displacement. So we can also check this effect by the physics validation. So this flow, first one shows the dimuon mass with two global muon. The green dot is before the muon alignment, and then red-green is the after alignment. So it became flat. And also PT resolution, the blue one has larger resolution width, but after that alignment, that became the usual one. And we can see a bit better the legacy geometry than the earlier geometry. Page 11 shows the legacy geometry. So 16, 17, 18 data, and their dimuon mass widths are stable and comparable. But at the higher eta region, a bit unstable due to low statistic. So page 12 explains the launch recombination plan. So CMS collaboration installed the GEM detector at station 1. So left figure, red detector is GEM at the station 1. And this GEM improved the tracking and trigger performance with the CSC detector. So right flow shows the GEM CSC bending angle calculation for the triggering. So that's why GEM CSC alignment also very important to get the correct trigger. So there is two GEM talks. If you have interesting, please attend that. And so muon alignment consider other method to improve the weak mode problem and also improve the alignment effect. So we have a plan to use the beam halo and cosmic muon data set to improve two topics. And we expect a large displacement of muon chambers during after LS2 because opening end cap and many the TT chambers are extracted and reinstalled. But TBMA method support iteration calculation, so we can expect a stable performance for the run 3. And the cosmic muon data set can help the initial alignment before the collision. So page 13 is a summary. So the performance of the track-based muon alignment in the run 2 was robust and stable, and it supported the muon reconstruction, and the CMS analysis used the many analysis used the muons. And run 3 workflow muon alignment has been prepared to include the gems, and after run LS2, there will be large displacement of the muon chamber, but we have a plan to with the initially correct them with the cosmic ray muons and then the PP collision later with MS2 inverse pentoband. Yeah, I'm done.
Okay, thank you. Questions to Yang?
If I
please.
might, I would, sorry, I would like to know if, how did you cope with the systematic effects? Did you have to, in the end, fix some degrees of freedoms for some modules or put additional constraints?
So of course they're limited by the hardware resolution itself to the limited, and the other systematic can be by the algorithm and the minimizer function. So it also related to the weak mode problem. So we did that, and also we prepared the Monte Carlo simulation to understand the systematic uncertainties. So we understand what is the systematics and their limit with the Monte Carlo study.
Okay, thank you. And what is the resolution of the modules, like intrinsic hit resolution?
Each DT, GSC, and their the station is different, but I don't know the details. But you can see the reference. You can see them in the reference. Yeah, here. So I recommend the reference one explain the details about the muon system.
Thank you.
Okay, other questions? Okay, you mentioned that you have 3 alignments per year. What is the change during from one alignment to another?
So we basically based on the tracker alignment. So if a tracker alignment the changes a lot, and then we divide the interval. So basically the tracker alignment has a more detailed interval, but we selected if the tracker alignment has changed their trend, then we did the muon alignment for that interval.
So you mean the change of alignment is due to the new track alignment? Yes,
correct. Because this TBMA, we are using the inner tracker track propagation to the muon system. So the muon system, their absolute position is not important, but between the tracker muon system, their relevant position is important to reconstruct muon track.
Okay, thank you. Okay, so let's move. Thank you once again. Let's move
to the
next presentation. It's Mohsen Nazari, small strip thin gap chamber and electronic performance for the muon spectrometer upgrade of the Atlas experiment.
Yeah. Okay. Hello, everyone. Can you hear me? And
yes, we can hear. Can see your slides.
You can see my slide. Okay. Okay. Hello, everyone. My name is Mohsen. It's my pleasure actually to be here to talk about one of the well-defined projects for the Atlas experiments. So on behalf of the Atlas Muon collaboration, I'm going to talk about the small thin gap chamber and also the electronic performance for the muon spectrometer of the Atlas experiment. On the second slide, just as an introduction, you all know the motivation for upgrade of the LHC is actually to provide more possibility for doing the standard model precise measurement and also to extend our sensitivity for the new physics search. To achieve this sequence of LHC upgrades are scheduled. For example, here the upgrade of the new the small wheel during the long shutdown period, and we expect to collect roughly 3,000 inverse femtobarn of data by end of the LHC operation in 2037. Why it's mandatory to replace our current small wheel with the new one? So the present wheel chamber will lose the efficiency at high rate, which we expect for the high luminosity phase, and this is because of the higher instantaneous luminosity. Actually, since the current muon system only use the middle wheel for triggering, so it won't be able to hold such rate. And if you look at the right plot, you see a lot.
I'm sorry to disturb you, but I'm not seeing changing the slides.
So I'm in slide 3.
But we just front page.
Yes.
Oh.
Maybe can you stop the sharing and maybe
yes.
you just don't share the full screen, but just the window of the
what about
application. Now it's fine.
Now it's fine?
Yes. Now we see slide 3.
Yes. Okay, good. Yeah, if you look at the right plot, you see a large fraction of the single muon L1 trigger currently originate from the forward region, and roughly 90% of this trigger actually are not originated from the interaction point. And if you look at the left plot, you see this spurious trigger are fake muon, which mostly consist of the low energy particle, which are generated in the layer between the inner station and the middle station, where we have the toroid magnet. On slide number 4, the proposal solution for moderating the L1 trigger without raising the associated PT threshold is by improving the muon identification in the end cap region. So we are replacing our small wheel in the end cap with the new one. And this new small wheel, it has been designed in such a way to significantly reduce the fake level muon trigger. And we expect to have more than 95% online track reconstruction efficiency. To achieve this goal, some strict requirement for the new small wheel has been defined. For example, we require to have the excellent online angular spatial resolution less than 1 millirad, and we need to have the good and efficient performance at round 3 and beyond it. Slide number 5. The new small wheel is a disc-shaped arrangement of the detector module, which is made of 8 large and 8 small pie-shaped sector. And we used 2 different technology to make this such wheel. So the micromegas detector, which are designed for precision tracking, and a small thin gap chamber, which are optimized for triggering. And each sector is made of 2 STGC wedges and 2 micromega wedges. And slide number 6, I just bring this few words about the new small wheel structure. As I said in my previous slide, we are using the STGC detector, and they are mainly used for triggering, but we also use them for the good tracking. This is because of the good timing resolution and also the small strip pitch. And this detector will provide us the 7-fold increase in rejection rate for fake muon triggers. And micromegas detector will be mainly used for precise tracking. They are also used for triggering, and it will reach us to the resolution better than 100 micrometer, independent of the track incidence angle. And a large collaboration has been established to construct the Quad. So the 5 countries, Canada, China, Chile, Israel, and Russia, are involved to construct a number of this Quad for the new small wheel. And this slide, and also the next slide, I will mainly focus on the STGC detector. The STGC chamber is a multi-wire proportional chamber that you see on the systematic diagram. An array of the wire are sandwiched between the two cathode board. On the top cathode board, we have the pad channel, and on the top side, we have the strip copper channels. And these STGC chamber are operated with the mixture of the CO2 and pentane. And when the particle goes through the detector, the ionization product induces a current on the wire, pad, and strips. And we will use these 3 channels as the active channels to get the data. To produce the high quality STGC module, so we need to finish the different stuff to complete the quad chamber. For example, we start from the graphite spraying, where we spray the cathode board and anode board. Then after the winding the pad board, we close the gaps, and after the closing gap, we assemble the doublets, and by merging the doublet, we will have the quadruplet. And for each of these steps, we have the quality test, which is done in different construction sites. For example, high voltage tests are completed at different stage just to identify any leakage current or spar. And one of the important step is X-ray scan, which is done in the single gap stage. We do this test to measure the gain uniformity and also to probe the internal structure of the gap, which I have shown here on the right plot. You see, if you look at the gain uniformity plot, we can probe the structure. Here you see the structure of the wire support and bottom, and also the level of the gain. And one of the check which we do in the construction site is the cosmic ray test. So we use the custom triggering, I mean the scintillator, just to record the hits. And these tests are conducted to check the efficiency maps, and also we can check the resolution and misalignment correction using such tests. And on top of this, the noise measurement can be also performed by using such setup. For example, on the left plot, you see the 2-dimensional efficiency of the strip channel for one of the QS3 gaps. And on the right side, you see number of the cosmic muon, which is counted for the QS3 gap. And if you look at the right plot on the corner, we have the less number of the counting of the heat. This is because of the limited coverage of the scintillator on the edge. And once we complete the quad, these quads are sent to CERN. And at CERN, we merge the 3 quad, we glue 3 quad to each other to assemble them to the wedge. And after making the wedge, so we put the Faraday cage just to prevent any interference from the outside to the detector. And after that, we install the electronic. And once we finish the electronic component, I mean the installation, they are integrated to the micromagnetic detector to make the sector and also the wheel. And at CERN, we also have some quality control, which are carried out at every step of the assembly. For example, we have the readout connectivity test to check the connectivity of all the strip, or pad, and the wire channels. And one of the most critical measurement is a stability test, which is done under high radiation using the one isotopic of the cesium, which radiates the gamma rays. So we use the G++ facility to do such tests. And there are some other quality tests, for example, long-term high voltage tests, when we construct the wedge. So on slide 14, so as I mentioned before, the precision requirements are challenging to achieve. Therefore, beam test experiments have been performed to check the quality of the detector. For example, on the left plot, you see the STGC pad charge distribution for different level of the background photon rate, which is measured using a muon beam in the presence of the high rate photon background. And also on the right plot, you see the result of also the charge distribution as a function of the high voltage. And for both plots, you see that we have the good discrimination with suppression of the noise from our signals. And one of the other measurement, which has been performed at CERN using our test beam setup, is spatial resolution as a function of the applied high voltage. To extract the resolution, so we estimate the residual distribution. The residual are decoupled to different components, to two different components. For example, the inclusive residual for a layer of interest is defined as the position difference between the layer space point and the position of the track, which is reconstructed using from the other layer. And the exclusive residual are obtained the same way, but they're reconstructing the track without the space point of the layer of the interest. And if you look at the right plot, for example, for the 2.8 kilovolt, which is the operational mode of the STGC detector, we have the resolution less than 100 micrometer. And this resolution is within the current muon momentum resolution in the end cap for the muon with 1 TeV GeV as a PT. And the STGC, the pad channel are used for the triggering. So to employ them for the triggering purpose, the pad layer are staggered to make the logical pad taller. And the triggering using the pad are completed in two independent steps. In the first step, 3 out of 4 layer with the heat required for the single wedge trigger. And the final decision will be based on the geometrical matching between the 2 wedge trigger, which we have in the outer layer of the STGC modules. And
I'm sorry, you have 1 minute left.
Yes, yeah. They are also used to define a region of interest that determine which group of strip need to be read out in order to obtain the precise measurement of from the strips. And as a conclusion, the new small wheel is essential for Atlas to maintain high trigger efficiency and momentum resolution in the high lob and the high radiation environment of the high luminosity LHC. The installation of the front end electronic on the wedge is ongoing well. And the STGC quadruplet production is underway at all construction sites. So it is complete for side A, for one side of the detector, and well underway for the other side. And the integration at CERN is progressing very well. And we have already completed 4 small STGC wedges with electronic, and all NSW large wedges have to be ready to install in sector by end of the January 2021. And the other side of the detector, I mean the NSWC side, has to be complete by October 2021. Thank you very much.
Thank you. Thank you. Questions to Mohsen?
Hello, can you hear me?
Yeah.
Yes.
Yes. Thanks for this nice talk. Maybe I just have a naive question. So you mentioned that the wires have more coarse resolution for the position compared to the strips, but they seem to be more closely spaced. So maybe a misunderstanding then why the strips are more precise than the wires.
No. I just wanted to say we will use the wire for the measurement of the 5 coordinated not the more precise. If I understand your question.
Okay, yes. No, I see your point. You're saying that the strips and wires they observe in two orthogonal views. Okay.
Yeah.
Okay, thanks.
Okay. Other questions? Oh, okay. On slide 15, you showed the dependence of resolution on high voltage. What is your working point? Is 2.8?
Yes, for the STGC detector, we actually for the quality test we will use the different level of the high voltage, but the operation mode will be 2.8 kilovolt. Yeah.
Mm-hmm. And increasing of high voltage leads to some instability, or?
Yeah. So that's why we have decoupled the residual distribution to the inclusive and exclusive. Yeah.
Okay, thank you. Okay, so let's move to the next talk of cosmic result with the final micromegas sector for the Atlas Muon upgrade from Gabriel. Okay, we can see your slide.
Okay, can you hear me?
Yes.
So hello everyone. My name is Gabriel Rabanal Bolaños, and I'm going to talk about the cosmic results with the final micromega sectors for the Atlas Muon upgrade. So this is the outline of this talk. I'm going to talk about the Nismel wheel, the cosmic array test stand, and everything we measure with it. So on slide 3, upgrading the Atlas Muon detector. So as you heard during the previous talk, the end cap detectors of the Atlas Muon spectrometer will be upgraded. And the places where the end caps are shown here in red. As you can see, we have side A and side C. The upgrade is not needed for the upcoming run 3 of the LHC, but will be needed for the high luminosity LHC. According to the Nismel wheel technical design report, the TDR, the Nismel wheel is expected to work at up to 15 kilohertz per square centimeter at a pseudo rapidity of 2.7, and a spatial resolution of 100 microns or better is needed for a momentum resolution better than 10% at 1 TeV, which is the resolution of the current small wheel. And you can see in the bottom right side how we need different sizes of detector chambers for overlap. These are called small modules and large modules, SM and LM. Now on the next slide, slide 4, we have the tracking technology of the new small wheel. So the previous talk was about the triggering chamber, so this is about the tracking. So this is a comparison of the tracking technologies of the small wheel at the left and the new small wheel at the right. So on the left side, you can see there's a cross-section of the monitor drift tubes, MDTs, which are still used in the rest of the Muon spectrometer. And on the right side, there's a cross-section of the micromegas detector, MM. So the micromegas detector is has a planar cathode and then a thin metallic micromesh. And the gas between these two works as an ionization region because there's a gas here. The gas is a mixture of argon and carbon dioxide. And the electric field here drifts the electrons towards the mesh. And then this region here is the amplification gap where we have the avalanche. So when a muon passes through, you can see there's ionization and then an avalanche here. And here we have the readout electrodes. So the electric field here in the amplification region is about 10 times stronger than in the drift gap. So the comparison is like this. So for the MDTs, the tube diameter is 2 centimeters, but for the micromegas, the strip pitch is 400 microns and the strip width is 300 microns. So we have smaller numbers here. This allows us to have better resolution. The maximum drift time of the MDTs is 700 nanoseconds, whereas for the micromegas, it's in the order of 100 nanoseconds. And the MDTs are used for precision tracking, and the micromegas is used for precision tracking, but also as a trigger. So in addition to the STGCs that were discussed in the previous talk. So in the next slide, we have the goals of the cosmic ray test stand that we have at CERN. So complete the final electronics integration of each micromegas double wedge or chamber, which looks like a pie slice. Test the data acquisition system, measure noise rate, high voltage, gas leaks, spark rate, sample the efficiency, get a sense of the resolution as well, and test a real detector with real muons. So on slide 6, we have, this is a cross section of a new small wheel chamber with a muon passing through the new small wheel here, through the trigger chambers in orange, and then the micromegas layers in green, which is the topic of this talk. On the right side, we have the different types of micromegas layers with the orientations of the strips in red here. So we have the so-called eta layers that measure the precision coordinate in eta, the pseudo rapidity, and also these other stereo layers that are tilted 1.5 degrees with respect to the eta layers to gather phi information. So on slide 7, we have the cosmic ray test stand at CERN. So 7 out of 16 small chambers, SM, were tested with cosmic muons with no minimum muon momentum. Each small chamber consists of 2 modules, SM1 and SM2, that are also shown below. And we have pairs of scintillators above that make a trigger with a frequency of about 100 Hertz and partially cover the chamber below. So you can see here on the left a side view of the cosmic ray test stand with the scintillators on top that we use for triggering on cosmic muons and the chamber below. And on the right side, there's a bird's eye view. So a view from above with the chamber here in green and the scintillators above it. It's worth noting that the scintillators do not cover the chamber uniformly. So they cover mostly the central part, and this will be seen later today. So our setup is not optimal for measuring high momentum muons due to the absence of an absorber and scintillators below the chamber. So in the next slide, slide 8, we have the baseline electronic noise. So on the left side, there's an event display. The axes are not at scale. So we can see a cosmic particle creating a track by inducing charge in 8 layers. So this red line is a reconstructed track, but also there's noise hits in different layers, as you can see here. So the first thing we do is to measure the noise. So on the right-hand side, there's an example of a baseline noise per strip measured in one front-end board, which you can see here, strip number in the x-axis, and here baseline noise. This is for 100 measurements. And from this, we can get the spread, the root mean squared, which is about 2.5 millivolts. And this RMS, this unit of the spread of the noise, is used to set up the signal threshold, RMS, RMS times 2, RMS times 3, etc. Because this changes from strip to strip. Once we measure the noise, then we can set up the strip threshold to decide when we get a signal. So, but first we have to try different thresholds to see how everything goes. So in order to trigger a noise, we delay the single signal from one scintillator. So we delay to avoid cosmic muons, and this is our trigger. So the higher threshold that we set must be selected first low enough to get a signal, but also high enough to keep the noise below the predicted hit rate at a high Lumi LHC, which is 1 kilohertz per strip. So on the right side, we have the electronic noise versus Harvard threshold measured in units of baseline RMS. And the noise rate falls as a function of the threshold. Given that we want our noise rate to be lower than the high luminosity LHC rate, we have to sit below this red line. And right now we are testing this setup, which is RMS times 9. And the effective charge threshold is 2.5 pentacoulombs. So this is an approximation of our current charge threshold per strip. So now that we set up the threshold, we can read our cosmic tracks, and we can see plots like this. This is a plot of cluster charge. So first we have a simple clustering algorithm known as Pacman that is used to group neighboring strips into clusters that are used to find tracks. But due to the high strip threshold that we have to set in order to have low noise, then we get single strip clusters, as you can see in this arrow pointing to this peak here. Also, you can see the way the place where it starts to rise, which is the threshold at about 2.5 pentacoulombs, which is expected. And also for straight down tracks, we expect on average 3 strip clusters. So what this means? This means that these single strip clusters are because we're not getting all the charge from a cosmic particle because we're setting such a high threshold, but they do have an important contribution to the overall tracking and efficiency calculation. So we cannot get rid of them. So we have to use them also. So on slide 11, we have tracks, which are the physics objects. On the left, you can see, again, another example of a track going through the 8 layers. And on the right side, we have a track map of one layer, 1 micromegas layer that we make when you consider all the points crossed by tracks that are reconstructed with at least 5 layers. The main point of this plot is to show that our data is biased towards the center of the chamber because of the scintillator acceptance. On slide 12, this is a summary of the high voltage configuration. Each micromegas layer has 16 high voltage sections. As you can see in this picture, 16 pieces. So the TDR had 600 volts as the nominal high voltage, but due to sparking, the new nominal high voltage was set to 570 volts for the amplification gap. So, and if a high voltage section sparks at a high rate, then its voltage is lowered and lowered and or turned off. So here on the left side, we can see an example of a possible configuration with one high voltage section at 550 volts, for instance, in orange, and everything else good. And for 7 small chambers tested in the cosmic ray test stand, roughly 89.6% are at nominal high voltage. This is fine, because even if we have sections that are not at nominal high voltage, we have 8 layers, right? So if one small section does not work properly, we have other 7 remaining layers that allow us to reconstruct a track. So this is fine. This is workable. So on slide 13, how we measure the efficiency with a tag and probe approach. So first we exclude the layer I, we blind it, then we fit a line using the remaining 7 layers. If a track is found, this is a tag. And then we unblind this layer, and if a cluster is found within a window of the track projection, then this cluster is a probe. The allowed window is 5 millimeters for eta layers and 10 millimeters for stereo layers. And the efficiency is just the number of probes divided by the number of tags, which is a counting process. On slide 14, we have the efficiency. So here's an example of a micromegas efficiency map for a layer at nominal high voltage, which is 570 volts. On the left, we have a 2-dimensional plot where you can see the efficiency in the fiducial region of 1 micromegas layer, with red equals an efficiency of 0 and green an efficiency of 1. And on the right side, we see the same layer, but this is the same layer, but this is just a 1D projection. So the same x-axis, which shows the efficiencies and the error bars. So here the axis is different. The axis is from 0.9 to 1. So we can see better the error bars in the data. So now this, since this is just for one micromegas layer with good high voltage, then we have to study how the efficiency changes when we have lower voltages because we have sparking and we have to lower the high voltage. So we make high voltage studies, which is this. So this is a plot of a micromegas efficiency versus amplification voltage, high voltage, for small chambers tested with cosmic muons. So we have many lines in this plot, and this is because these are the results of various layers that could all hold nominal high voltage without sparking. This allowed us to lower or raise the high voltage at will. And this gives us a sense of the dependence of the efficiency of a good layer as a function of a high voltage. So at the very bottom in blue, we have the percentage of high voltage sections that are at each high voltage configuration for the 7 small chambers that have been tested so far. So here we can see 89.6% are at 570 volts, which have like a nominal efficiency of about 94 to 96%. But even if you lower it up to like 550, then the efficiency is about 80% or more. And sorry, again. So I want to repeat again, this is not a problem. This is fine as long as the sections with low high voltage do not overlap on top of each other. Because remember, we have 8 layers. So if one high voltage section has low voltage or is turned off due to sparking, we have 7 remaining layers that do the tracking. And we never have more than 2 high voltage sections turned off that are overlapping each other. And on slide 16, we have the residuals. So an unbiased residual is defined as the distance between the intersection of a track with a layer, but created by blinding that layer. So not looking at what any cluster in the layer, and then the centroid of the closest cluster in said layer, if any. So at the left-hand side, you see the plot that I showed earlier, showing how we blind one layer to find the track with the remaining layers. And then we find the residual of the cluster in this layer with respect to said track. And on the right-hand side, this is a sample of the distribution of all such residuals. But this is for tracks whose incident angles are less than 5 degrees. So this is mostly vertical tracks that go perpendicular to the chamber, so that we were testing. So it is centered at, So it is centered at 0. And it has a Gaussian-like spread, which is expected from a tracking detector. And you can see a simple Gaussian fit in red. It is worth noting that the spread of this distribution is not only the resolution, but this also includes the effect of multiple scattering and extrapolation error. So the true resolution of the chambers are actually a work in progress and need further investigation. And finally, on slide 17, a complete electronics integration with the final chambers has been done with cosmic rays and it works. 7 small chambers out of the 16 were tested with cosmic muons at CERN. And no large chambers were tested yet at CERN. We determined many sections, how many sections hold high voltage, and the efficiency of each layer was measured. And also the projected timeline for this, as per the latest NISMO wheel review meeting on July 20th, was that the commissioning of the NISMO wheel site A is projected to finish by May 2021, and the NISMO wheel site C by October 2021. Thank you very much for your attention.
Thank you. Question to Gabriel. Okay, I have question about sparking. As I understand, the sparking is quite critical. Do you observe some changing of sparking rate with time?
A change of sparking rate with time? So I don't know the answer to that. Yeah, I mean, as far as I know, we have a very dynamic definition of sparking. Right now, if anything goes above 40 nanoamperes, then that's considered a spark, and then we start measuring how many sparks per minute we have. If the spark is more than 5 per minute, I think then we lower the voltage. But I don't know the answer exactly to that question. But I can look it up, and I can also write it to you afterwards.
Okay, if there are no other questions, let's thank Gabriel and all speakers of this session. So now we have a break. We 5 minutes late, so let's meet within 5 minutes. 5:25 for next session. Please, speakers who will do the presentation next session, check the Zoom operation during coffee break if you have not done it. Thank you. See you within 5 minutes.
Hello, can you hear me?
Yes.
Yeah, I see Gabriel speaking, maybe still, but muted. Oh, sorry.
Okay, so I think we have already time to start. So let's start next session. We have quite tight schedule, so please be within the schedule. So let's come to luminosity measurements with Atlas experiment at LHC. So we can see slides.
Okay, good. Yeah, I'll get started then. All right, well, thank you. It's a real pleasure to be here. So my name is Joey. I'll be giving an overview of Atlas's luminosity measurement in run 2. So first, I'll start with a brief introduction and motivation for why we care about precision luminosity measurements at the LHC. So it's important for both online and offline measurements. So for online luminosity measurements, an accuracy of roughly 5% was achieved in run 2. And this accuracy was required for operating the accelerator and for operating the detectors. So for example, for performance optimizations, leveling, and trigger optimizations. A precise offline luminosity measurement is particularly important for all analyses, but especially for precision cross-section measurements. So an example I've given here is the ratios of top cross-section measurements. So you can see from the green band how large the luminosity uncertainty is. And a luminosity of uncertainty of 1% would be required to make it subleading amongst other well-controlled systematics. So new for ICHEP, Atlas has also just released new luminosity results on the 13 TV low mu and 5 TV low mu data sets. The motivation for these data sets was to provide data for precision W boson measurements and also to serve as proton-proton reference data for the heavy ion program. So here's an overview of the run 2 proton-proton data sets with some tables of typical running conditions. So for 13 TV high mu, we have these running conditions here. And for low mu, we have the typical running conditions here. For low mu, these runs were typically leveled to average number of interactions per bunch crossing, or mu, of 2 or 1 in 2017 and 2018. And here on the plot on the right, the bottom right, you can see the 13 TB low mu data set in this little bump at low mu, which is a plot of recorded luminosity as a distribution as a function of the mean number of interactions per bunch crossing. Okay, so here's the basic idea of measuring luminosity at a Hadron Collider. So luminosity is given by the event rate divided by some quantity, sigma vis. So R here is the event rate. That's the event rate that some detector measures. And sigma vis is, or sigma visible, is the visible cross-section that detector sees. So it's effectively that detector's calibration constant. So here we'll focus on the event rate measurements. So the primary Atlas luminosity measurement came from Lucid. So Lucid uses a hit counting algorithm using Cherenkov light radiation from quartz windows, provided bunch by bunch measurements. And these are integrated over luminosity blocks, which are typically 60 seconds, and use a hit counting algorithm of these photomultiplier tubes for the offline measurement, and used sort of an OR algorithm of either side, 4 PMTs on either side of the detector. Lucid was complemented by several other detectors in Atlas. So first is track counting. So this uses the multiplicity of reconstructed charged particle tracks in the silicon layers of the inner detector. You can also use calorimeter data. So you can use the electromagnetic ENCAP or EMEC and the FCAL for the forward calorimeter. These are liquid argon sampling calorimeters, and then the proportions or the quantity proportional to luminosity is the LAR gap current. You can also use the hadronic tile calorimeters. Here we use scintillating tile PMT currents as that quantity proportional to luminosity. Okay, so now that we have an event rate, it's all a matter of calibrating that event rate to get a luminosity. The method that Atlas uses is the Vandermeer scan method. So the basic outline of the Vandermeer scan formalism is as follows. So you get the per bunch luminosity LB from the bunch revolution frequency FR, and the bunch populations N1 and N2, and finally the integral over the proton transverse density distributions, so these rho hats, as a function of X and Y. The next step is to scan the beam separation delta X and delta Y in the X and Y planes respectively, and then compute the overlap integral to extract the convolved beam sizes, or this capital sigma, or cap sigma for short, that quantity here. So on the top right plot, this shows a typical Vandermeer scan session. So you can see beam 1 and beam 2 being scanned in X and Y, or X on the top plot and Y on the bottom part. And then the bottom plot shows a typical scan curve. So this is the event rate as a function of the separation delta X. So the scan curve is fitted with a Gaussian times polynomial to compute the overlap integral, and we try different fit functions and then take the difference as a systematic uncertainty. So with that scan curve, we can then take the integral here, as we show in this equation here, normalize it to the rate at the peak of the scan, so to get a quantity that, or dimensionless quantity, and then rewrite this in terms of the number of interactions per bunch crossing, or the maximum interactions per bunch crossing visible to that detector. And then from that, we can calculate the calibration constant sigma vis. Okay, so here's some details and sources of uncertainty from the Vandermeer scans. So the first I highlight is the scan-to-scan variation. So we expect to get the same sigma vis for different bunch pairs and scan sets. And then, but of course we don't, so we take the maximum difference between the extremes as an uncertainty. And this is what the plot on the right shows. So in 2017, this gave rise to a 1.2% uncertainty, although it's typically half that in other years. There's also the length scale calibration. So this is the relationship between the nominal, or in other words, the requested beam displacement and the actual beam displacement at the interaction point. This typically gave an uncertainty on the order of 0.3 to 0.4%. These are dominated by orbit drift corrections and magnetic hysteresis effects. Here on the bottom right, I've highlighted another important correction from non-factorization. So the Vandermeer scan formalism assumes that you can factorize these beam profiles into X and Y components, but this of course isn't actually true. So we need to correct for this. And the way we do the correction is to apply or do combined fits to the beam separation dependence of the luminosity and of the parameters of the luminous region in three-dimensional space. And then we do fits in both on and off axis VDM scans. So this typically leads to a correction factor less than 1% and uncertainties of roughly 0.2 to 0.5%. I've highlighted another correction here from beam effects. So those are the electromagnetic interactions between bunches. So there are two main effects to correct for. First is from optical distortion. So that's the defocusing of one beam by the other beam. And sometimes this is also called the dynamic beta effect. There are also nonlinear distortions of the intended beam separation. So these are the two effects we correct for. The treatment of these corrections is under review. So the correction on sigma vis had previously been overestimated by 1% up until 2019, which was one of the things highlighted at the LHC LumiDays workshop, which I've provided links to in the backup slides. So for the 13 TV data sets, we still use the original correction of plus 1.3 to plus 1.7%, depending on the scan. So to be looked into in future work. But the 5 TV data sets that we've also looked at use the updated correction, which give an upward correction of 0.2%. So the next procedure in the calibration of the main luminosity algorithm from Lucid is the so-called calibration transfer. So that's to bring the calibration that we obtain in the Vandermeer scan regime to the physics regime. And the reason we have to do this is because Lucid overestimates the luminosity by about 10% in high mu physics conditions. So some of the differences in conditions from Vandermeer's to physics, so going from low mu to high mu, going from isolated bunches to trains, and an overall increase in the number of bunches, and from zero crossing angle in the Vandermeer scan to nominal physics crossing angles. So the way we correct for this is to parameterize it in terms of mu with respect to track counting luminosity, fit a straight line to it, and then correct the lucid luminosity from that. So this is what this plot shows on the right, the ratio of track counting luminosity to lucid. as a function of mu. This, of course, assumes that track counting is inherently linear with mu, and we need to verify this assumption. So the way we do that is look for another detector that's sensitive over these large dynamic ranges from Van der Waals to physics. And for that, we use the tile E cells. And then what we do is compare the tile over tracks ratios in the Van der Waals fill, so in this part here, and a closely following physics fill, so this part here. There's a relative 1.3% nonlinearity between the two, so we assign this as an additional systematic. At low mu, calibration transfer is still required, even though the range in mu is smaller. And of course, because the range in mu is smaller, the size of the correction is smaller as well. So this plot shows, again, ratios of track counting to lucid, and there's about a 1.51% correction to make there. Next is the long-term stability. So this is where we monitor lucid throughout each data taking year with respect to other luminosity algorithms. And then we assign a stability band uncertainty to enclose the bulk of the points. So in the high mu data sets, the largest stability uncertainty at 13 TeV came from the 2017 running year. This gave a 1.3% uncertainty, which is shown by the yellow band here. It was smaller in other years, 0.7% in 2015-16 and 0.8% in 2018. At low mu, the stability uncertainty is smaller overall, on the order of 0.4 to up to 1%. And this is thanks to data being taken over a short period of time, so typically 1 to 2 weeks, and ideally close to the Van der Waals fill. So this is what these two plots on the right show. So that's long-term stability at 5 TeV on the top, and long-term stability of 13 TeV low mu on the bottom. So now that we have all these uncertainties and measurements of luminosity, the next step is, because analyses treat data sets with common center of mass energy and running conditions from different years as a single combined data set, we need to then combine the luminosity and their uncertainties, accounting for inter-year correlations. So this is what we do. We tabulate all the uncertainties, account for these correlations I mentioned, and then we arrive at an uncertainty of roughly 2% each year. And when we do the combination, we arrive at, for the high mu data set, a final luminosity uncertainty of 1.7%. And for the low mu data sets, the final uncertainty is about 1.5% for the full data sets. I've highlighted here the calibration transfer uncertainties. So this was overall the largest uncertainties. So the next steps are then to better understand this calibration procedure and reduce the uncertainty here. And this is what the next slide shows. So one possible avenue of improvement to improve the calibration transfer uncertainty is to look more deeply into track counting luminosity, because of course the calibration transfer relies on track counting to make to make the correction. So the performance of any track counting algorithm depends on the choice of track selection working points. So what we're doing now is investigating other working points. So for example, changing the requirements number of silicon hits, and this is what this plot shows. So the selections used in 2017 plus an additional silicon hit with respect to the baseline 2017 selections. And what this does is provides a means to monitor the stability and internal consistency of the track counting measurements. Another thing we can look at is Z boson counting. So the Z boson production rate at the LHC is sufficiently high that counting Z bosons, yes, counting Z bosons can act as a luminosity meter. It serves as an additional check on the stability of the primary atlas luminosity measurement from Lucid, so this can help understand that. Finally, I have another effect that we've observed in run 2, which is calorimeter activation. So running with head-on collisions activates the calorimeter materials, and this leads to an artificially high luminosity measurement that gradually decays over time, typically over a few hours. And this is what this plot shows on the left. So it's important to understand these effects for both the calibration transfer and the long-term stability. And currently we're exploring both data-driven and simulation-based approaches to model and correct for these effects. On the last slide, I show a summary of the run 2 data sets with their uncertainties and links to the relevant documentation. And finally, I've highlighted a couple of, or 3 luminosity posters at ICHEP from Atlas. All right, thank you.
Thank you. Questions to Joy?
Maybe I would like to ask if the new tracker, inner tracker planned for Atlas for high luminosity can help with this.
Oh, I imagine it would. Off the top of my head, I can't think of any studies, explicit studies that have been done for that. But right now we're focusing on improvements for run 3 and the final uncertainty for run 2.
Perhaps I can comment on this.
Okay.
The new tracker will use track counting as we do now. We will develop pixel cluster counting, which is one of the main CMS algorithms. And we will also have some dedicated sections in the tracker to pixel cluster counting at very high rate for luminosity. This is something we cannot do in the present tracker TDAC infrastructure, but it will be possible at HLLHC.
Okay, thanks.
Thank you. Other questions? Okay, if not, thank you. And next, let's move to the next topic. It's CMS track reconstruction performance during run 2 and development for run 3. Will be performed by...
Hello, everyone.
Okay, we can see your slides.
Okay, thanks.
Please go ahead.
Hello, everyone. I'm going to talk about CMS track reconstruction performance during run 2 and developments for run 3. Typically, we have 30 charged particles within the tracker acceptance per proton-proton collision, and between 25 to 40 collisions per event. So in total, we have around 1,000 charged particles per event need to be reconstructed. And this is the tracking challenge at LHC. And to reconstruct these particles, we have the largest silicon tracker ever built, which cover active area 200 meters square and the acceptance abs eta less than 2.5 and immersed in 3.8 Tesla magnetic field. Our CMS tracking system consists mainly from 2 detectors, strip detector and pixel detector. As you see here in this figure, this is the layout of our CMS tracking system during run 1 and run 2 2016. And then to cope with increasing the luminosity during run 2, we had the tracker upgrade in 2017. As you see here in the bottom figure, the comparison between phase 0 pixel detector and phase 1 pixel detector, where you can see the original pixel detector replaced with new device phase 1 pixel detector to address the dynamic inefficiencies in readout chip at high rates. We can conclude these improvements in 3 points. One additional tracking point in both parallel and forward regions, and this allows us to reconstruct 4 head seeds and give us lower fake rates. Also, a smaller radius of innermost pixel layer, and this makes us closer to the interaction point and improve our tracking and vertexing performance. And also reduce the material budget, and this reduces the multiple scattering and photon conversion. To reconstruct our track in CMS, we are following iterative procedures, where our iteration is starting here, and the first step is to provide an initial track candidate and trajectory parameter in the seeding layer. And then we extrapolate our track to the next layer and find compatible hits and update our filter. We are continue until there is no more layer or there is more than one missing hit. Then to provide the final fitting, we provide best estimation of parameters of each smooth trajectory after combining all the associated hits. And finally, for the track selection, we are following a set of cuts sensitive to the fake rate and also the track normalized chi-square and on its compatibility with the interaction point. Then we remove all the hits of the found tracks, and this is reduced for us the combinatorial problem so that we can reconstruct a more difficult track within the CPU time budget. And then we start our iteration from the beginning, but this time with progressively looser setting. As you see here, our 12 iterations summarized here in this table, where we start with the high PT tracks, which is prompt track, have high precision, pixel hits, and beam spot constraints. And then we use triplet seeds. And then the later steps use head from the strip detector to find ditch tracks. And the final step use special iteration to improve the track reconstruction in high dense environment like reconstruct the track inside jets, or use information from other subsystems like MEONs. You can see here in the bottom plots our tracking efficiency per each iteration as a function of simulated track BT and simulated track production vertex radius. Then, following the improvement done in 2017, we also had new track seeding algorithm based on cellular automaton technique. In CA technique, the head pairs formed between detector layers, and then the pair compatibility with the interaction point is checked, and finally, the triplets or quadruplets that used for seeding are formed from the compatible pairs. You can see here in the bottom plots comparison between the performance during 2016 and 2017 using the CA. As you see, we have increase in the efficiency and decrease in the fake rate, and also improve in the BT resolution, especially in the transition region between the barrel and the end cap. Also, we have improvement in the timing. Actually, with additional layers in the pixel detector, we would expect slowed down track seeding with using a conventional seed finding. But using the CA reduce the timing, as you see here in the left plot, back to or even below 2016 performance. Also, the reduction in the fake rates that we showed in the previous slide make reduction in the time spent on pattern recognition, as you see here in the middle plot, and this is independent of the seed algorithm. So in total, we have around 20% faster track reconstruction, as you see here in the right plot at high pileup, despite the increase in the number of pixel layers. Then looking at the tracking performance in run2 legacy data, you can see here in these plots the tracking efficiency in run2 legacy data with the total integrated luminosity 137 inverse femtobarn, where you can see in the left and the middle plot, we have tracking efficiency almost 99.9% despite all the challenges we had in run2. So thanks to the long shutdown one improvement and also during run2. And if we compare the different era for run2, we have here good agreement in the right plot. We have good agreement between the tracking efficiency for 2018, 2017, and 16 new ABV settings. And we have loss in the efficiency up to 2% found for 2016 old ABV settings. Looking at the track impact parameter resolution, as you see here in the top plot, we have a comparison here between the 2017 vertex reconstruction and 2016 one. And as you see, 2017 vertex reconstruction show better performance than 2016 one. So thanks to the new pixel detector. And as you see here in the bottom plot, this is the transverse track IP resolution in 2017 legacy data with phase 1 pixel detector as a function of track transverse momentum and the track eta. As you see, we have for BT between 1 and 10 GeV and APS eta less than 2.5, the resolution between 20 and 75 micrometer. And for APS eta less than 1.4, we have resolution between 20 and 65 micrometer, which is much better than phase 0 pixel detector. Then the tracking reconstruction at high level trigger, our tracking at HLT is regional tracking. I mean, we reconstruct the track around physics object. And due to the time constraints at HLT, we reduce the number of iteration with respect to offline tracking. Here you can see in this table example for CA seeding for BF at HLT, since 2017, we have only 3 iterations. But during operation in 2017, we had several issues with phase 1 pixel detector, and this led to non-negligible fraction of non-active pixel modules in each event. And so in 2017, we adopted the static mitigation via dedicated iteration in specific eta and phi regions. But the recovery was insufficient for additional dynamic pixel issues. And so in 2018, we adopted the dynamic mitigation of the pixel issues. And as you can see here on the right, the HLT tracking efficiency is almost matching to the ideal efficiency. And also we have efficiency is flat, almost flat as a function of pileup. Then turning to the developments for run 3, actually with increasing the luminosity and consequently the accumulated radiation, there will be non-negligible degradation in our tracking detector in both pixel and strip detector with respect to the nominal performances that we have now. So there are new developments targeting run 3 is ongoing now. Like developments in the mitigation strategy and also developments in the track selection and the developments in track seeding in dense environment like track seeding inside jets, also in the seed cleaning. So let's try to discuss some of these developments now. Here you can see the improvement targeting tracking inside jets. Actually, tracking inside jets become inefficient if we go over 500 Gs due to cluster merging. And so we have some developments targeting run 3. As you see here in the flow chart, we aim to skip the clustering and using the pixel clustering and using the convolutional neural network to produce track seeds in jets. So our input here will be the pixel row info, the 4-layer pixel row info, as you see here in the bottom plots, and plus jet BT and eta from the calorimeter. And our target here will be track seed parameters. Actually performing this test show us, as you see in the left plot here, efficiency which almost matching the Monte Carlo truth seeding, which is of course will be ideal efficiency. And also we had fake rate reduction around 60% and also seeding time reduction around 85%. Then, following the developments for run 3, we also have developments targeting seed filtering. As we discussed before, the track seeding, as you see here in the flow chart on the right, the track seeding in the pixel detector start with head doublets, and then we form the triplet and quadruplet to build seeds. What we aim to do for run 3 is starting from this doublet generation, we will filter the pixel clusters based on their shape using CNN. So our inputs here will be the maps of of pixel clusters for the hits making the doublets. And performing this test show us almost any change in the performance of the downstream track reconstruction. And as you see here in this plot, we have fake rate reduction around 40%. And also we have time reduction here around 68%.
Okay, you have one, okay.
Yeah, okay, the conclusion. Okay, so we can conclude what we discussed in that. Despite the challenging condition we had at LHC in run 2, we have high tracking and vertexing performance, which depend on the performance of the detector as well as the algorithm used in the event reconstruction. Also, we can say that phase 1 pixel tracker helped us to cope with the large increase in the luminosity and the pileup events. And we can say about HLT tracking, it was efficient. We have new developments targeting run 3 to cope with increasing in the luminosity and in the rate. Which mainly in the mitigation strategy and in the track selection, where we aim to use a deep neural network for our track selection. And also we have developments targeting track seeding inside the dense environment like in jets using a deep core and seed cleaning using CNN. Thanks.
Thank you. Questions to all? Okay. I have questions for run 2. You have excellent efficiency, but for run 3 you expect degradation. So what is target efficiency for run 3?
We aim to keep with the same excellent efficiency for run 3. For this reason, we are trying to do developments in the track selections and in also to development our mitigation strategy and so on. So we target to cope with the same excellent performance even during run 3. And actually, our results up to now from the developments for run 3 is promising results. So we hope so.
Okay. So you are not expecting reduction of efficiency even after accumulating full luminosity?
Yeah, I hope so, yes.
Okay. Okay, thank you. I don't see questions. Okay, so thank you. Let's move to next presentation. It's CMS electron and photon performance at round 2 and prospects for round 3. But Olivia, Sophie?
Yeah. Hi, can you hear me?
Yes,
and
please
you
go
should
ahead.
you should also see me, maybe?
Sorry?
Do you also see my video?
Yes, yes, we see your slides.
Okay, you should also see my okay, perfect. Okay, so thanks a lot. In this talk, I will explain you the performance that at the moment have at CMS for concern reconstruction and identification of electrons and photons. So as you know very well, electrons and photons are key ingredients for many analyses in CMS. And this is possible only because we have a strong interplay between calorimeters and tracker, and we are able to reconstruct these objects with a very high precision and purity. The results that I'm going to show you today, they include the full run 2 data, 16, 17, and 18. And for 2017, we present the legacy version of the data, which means data with a finer and better improved calibration, which allow us to get a better data Monte Carlo agreement and also very good performance in terms of resolution. In any case, also the performance of 16 and 18 are very similar to 2017 legacy. And as well, at the end, I will show you an insight of run 3 preliminary results. So as you know, the CMS detector is a very complex subject with many sub-detectors, but for what concern electrons and photons, the two main sub-detectors which are relevant here are the inner tracker, which has been just very nicely described, where the main improvement is related to the upgrade that we had during the previous long shutdown. And now we are able to use a more complex information of the pixel detector with more layers. And this really makes a big difference, as I will show you in the next slide. And then, obviously, the electromagnetic calorimeter of CMS, which is made of lead tungstate crystals, which is able to provide us excellent performance. And also in this case, I'm not going to describe the detector because already the previous talk has been very nice on this, and there is also a poster which I invite you to visit to have more details. So here, just in 2 sentences, all the excellent performance that the ECAL provides to us, perfect energy resolution between 1 and 5%, and also surprisingly a very good timing resolution of roughly 200 picoseconds. And these 2 numbers allow us to do very nice studies. And this is kind of a summary of the main results that you are going to see here in this conference related to electrons and photons. The X decays in ZZ and the then electrons, or the X in diphotons, but also searches for new physics with some non-conventional signatures, which in this case, for example, are delayed jets that exploit the timing measurement in the ECAL. So first of all, everything starts from the collection of the signals in our crystals in the detector. At the moment, the reconstruction of the signal amplitude is done since 2015 with a new method that is called template method, where we somehow take into account and subtract the information of the out-of-time pile-up, and we get a much better estimation of the energy deposited in the crystal with respect to the previous method that was used in the round 2. In this case, you can see that in the plot on the bottom, the resolution, the energy resolution improves a lot by a factor by roughly 50%, especially at low energy where the out-of-time pile-up is more important. Then what we have to do, we have our signals in the ECAL, we have to reconstruct the objects. So at this point is where the tracker enters in the game, because there is a strong interplay between clustering in the ECAL and the reconstruction of the track in the tracker. We have dedicated algorithms to do that. For the clustering, we exploit the shape of the energy deposits in the detector. For the tracker, we apply the Gaussian sum filter algorithm. And in this way, we are able to reconstruct with very high efficiency both electrons and photons. These algorithms are applied both online and offline. And in addition, there is also a dedicated algorithm to collect the energy spread in the transversal plane due to the presence of the magnetic field, which bend the charged particles. So as I was saying to you before, the presence of the new pixel detector is very important because it brought us a huge improvement. For example, in this plot, I show you the improvement in terms of fake rate as a function of the number of pile-up. In green, you have 16, which means the old pixel detector. In blue is 17, the new detector. You see that we have an improvement of roughly 30% as a function of the pile-up. And also, as I was saying to you, the efficiencies in the reconstruction are very high, bigger than 96% over the full PT spectrum. At HLT, performance is also very good. In this case, we tested the efficiencies of one of the many electron or photon trigger paths that we have. And as you can see, the efficiencies are stable in time, which means that they are not affected by the detector aging, and they are very good both in terms of pile-up, but also in terms of energy. In this case, I'm showing a reference trigger with the double electron requirement. For what concerns the offline reconstruction, after having built our clusters both for an electron and for a photons, we have to correct the energy measurements for many effects. We have a multi-step procedure. The first procedure is a multivariate technique in order to correct the energy itself of the object. And then there is a second step where we apply residual corrections using the Z boson mass. We basically scale shift the data to match the position of the peak of in the Monte Carlo, because that is the truth. And then we smear the Monte Carlo to match the resolution that we observe in data. There is a significant improvement in this procedure with respect to run 1 because we are doing this correction with a very fine granularity. And in addition, there is also another correction applied for very precision analysis, like for example, this to gamma gamma as shown here, where this correction is also applied as a function of the energy in order to correct further the residual disagreement between data and Monte Carlo. So here you have the performance of the energy resolution. As you can see, we get a very nice agreement in terms of the data Monte Carlo comparison for the Z mass peak. This in this case is 2017 data. But also, if you look at the plot on the right, the resolution in the mass and the electron decay for the Z is within 1 and 4% over the full eta spectrum. And this is true for all the years, clearly. For the 2017 legacy, we observe a better resolution, but all the 3 years provide us a very solid and good quality results. Then, after having measured the energy of our objects, we have to identify the objects, the electrons and the photons. We basically have 2 main strategies. One is to exploit the shape of the energy deposits in the calorimeter. Another one is to exploit the isolation, so the amount of energies around the direction of the electron or photon in the tracker, the e-cal or the hadronic calorimeter. At CMS, we have several working points, several kind of selections for both electrons and photons. We also have two different approaches, multivariate one and a cut-based approach. The cut-based is most relevant for exotic searches where you really don't want a model-dependent selection. And as you can see in the plots here, we have the raw curves for the MVA working points, but also reported here the several working points for the cut-based. In addition to this, we have also a couple of dedicated identification requirements, either for displaced objects or for very high energy electrons or photons. So for what concerns the performance of the identification, what I want to stress here in the plot on the left is the improvement in terms of theta Monte Carlo agreement for the identification efficiency, where the correction factor to Monte Carlo were roughly 90% in 2017. With the new legacy calibration, we managed to get an improvement of roughly 5–10% in terms of agreement between data and Monte Carlo. The plot on the right here shows you the agreement again between the 3 years of full run 2 for what concerns a specific working point, but still also in this case, both efficiencies and data Monte Carlo corrections are very consistent among the years. Then, as I was telling to you, there is also another important aspect of the e-cal detector. We are also very lucky that we can use this detector to measure very well, not only the energy, but also the timing of the particles hitting the calorimeter. We measured the timing resolution of the full run 2 data set, and we got a resolution of roughly 200 picoseconds for energies above 30 GP. This number is not the 30 picosecond that we expect for the high Lumi phase, but still is a very good ingredient and allow us to perform searches for new physics. For example, in this plot, I show you the timing distribution that you expect in data, so something around 0 within the quoted resolution, but also the timing distribution that you expect for photons arriving in delay on the detector coming from a scenario of physics beyond the standard model. So you can see already from these plots how powerful is this information in order to search for potential signals of physics, of new physics. In addition, we are also exploring new phase space regions. So at this point, we are also dedicating a lot of efforts to low PT objects. This is very important because low PT electrons are very common in B-physics searches, but also I would say in exotic searches. For this reason, our experts have developed a dedicated reconstruction algorithm with a new seeding strategy able to recover the reconstruction efficiencies at low energy, so this means below 2 GeV, from basically 0 up to 60%. And this is very good because it allows us to explore a new and unexplored region of energies also in our physics searches. And finally, run 3. So for run 3, as we have already said, we expect a much harsher environment at LHC, much larger pile-up, and also a lot of more noise in the e-cal crystals. And obviously, if the noise increases, we have much more rekits in our cluster, in our energy deposits that we should consider or not when we studied and we construct our electrons and photons objects. This means that if we mistakenly include wrong rekits in our objects, the performance of the reconstruction and the identification decreases. For this reason, our experts at the moment are developing new superclustering strategies in order to apply some noise cleaning and recover the performance in terms of reconstruction and identification that we have now around 2. And these strategies are based on, again, multivariate based algorithm. So in the specific, I just give you here an example.
1 minute left.
Yes, it's finished. I just give you here an example where we have an identification variable that we use very frequently, which is called sigma eta. In this case, the shape that we expect is the red one for run 3 with the correction applied with the new reclustering will be the blue one, and we will be able to recover the performance in terms of background rejection that we have at the moment now in run 2, which are here in green. In addition, let me comment that we will also have a new HCAL detector that will allow us to perform new way of identification also in the case of electrons and photons exploiting the layers of the HCAL. This brings me to my conclusion. I hope that I convince you that the performance that CMS at the moment has for electrons and photons are very good, that there have been many improvements starting from the new template method for the clusters, for the signals, up to the new recalibration of the detector. And we are preparing now at the moment a paper on run 2 that is going to be released in summer. I want to finish showing you this very nice plot that has been approved very recently in CMS, which show you the performance in terms of energy resolution for the 3 years, but this time also 2016 and 2018 are presented with the legacy calibration, so with the very final calibration. So we can say from this plot that this is the best that CMS can provide at run 2 in terms of energy resolution for electrons and photons. Performance again are stable over the 3 years, and these numbers really are very promising in terms of performance for physics analysis that will be released in the next months. Thanks.
Okay, thank you. Questions to Olivier? Okay, so let me ask questions. You show very nice figures that your resolution doesn't depend on ear, and practically no degradation expected to the very high eta region. What do you expect for run 3?
So for
some degradation?
So for run 3, let's say the purpose is to develop the new superclustering algorithm that I was mentioning to you before in order to recover the run 2 performance. So what we expect is that with the new tools that people are developing now, we will be able to match the performance that we have here.
So you expect to get the same resolution, about 2% for...
Yeah, between 2 and 5, yeah.
In spite of the radiation damage and so on.
Yeah, I mean, that is exactly the point, is to try to tell the tool should be able to learn itself from the performance of the kits how is the best way to cluster the objects in order to match the performance that we still have. And this is valid also for the identification. For the identification selection, we are trying to target the same efficiencies that we have now with the new definition of the new variables when needed.
Okay, thank you.
Thank you.
Okay, so let's move to the next talk, CMS jet and missing transverse momentum performance at round 2 and prospects for round 3.
Hi. Can you hear me?
Yes.
Can you see also the slides?
Yeah, we can see slides.
Okay, so I will be giving a summary talk about reconstruction and calibration of jets emitting transverse energy in the CMS collaboration. So during round 2, a lot of data was collected by the CMS detector with the average pileup of 30 interactions per bunch crossing. And our ultimate goal is to achieve the best performances for both jets and missing transverse energy. And to do so, we use a plethora of techniques to handle the challenge of very different pileup scenarios. And as you can see on the right-handed plot, we collect data up to 6 interactions per batch crossing, and the expected pileup for the upcoming run 3 is even higher than what we had so far. And we're getting ready to face this challenge, as I will show you in the next slide. Okay, so let me jump directly into the chain used by CMS for reconstructing jet and missing transverse energy. This scheme is used for both the online and the offline reconstruction, with some differences in the amount of the information that is used or the level of correction that is applied, just to achieve a fast performance during data taking. So we start from a local reconstruction, which means that we combine information in each subdetector. And here it's very important to be fast for the online reconstruction. And in the future, the GPU will handle this task. The next step is what we call particle flow. We use all the quantities that are reconstructed in the previous step to identify the particle composition of each event. And already at this stage, some of the pileup mitigation techniques are applied. Afterwards, we start the reconstruction process, which consists of the clustering of all the particle flow candidates into jets. And we use a variety of clustering algorithms and cone sizes. And only at the very end, we deal with the final calibration of our jets. We propagate the correction into the missing transverse energy, and we can also apply additional pileup cleaning. So in proton-proton collision, multiple interactions happen in the same time. And additional particles that are produced can deteriorate the measurements since they may end up in the reconstructed jets. And here there is a sketch where we have pileup contribution in those jets. So getting reading of pileup is an art, and there are a variety of techniques one could use. And one example is the CHS algorithm, which uses information from the detector to remove the charged particles that are associated to a pileup vertex. But the target coverage is only limited in eta. So outside the tracker, we don't know really the charge of the particle. So to account for the effect of neutral component, we take care of this in the jet energy correction, as I will show in the next slide. Moreover, to reduce the effect of the neutral component, CMS uses as an alternative the PAPI algorithm, which assigns each particle a weight corresponding to the probability of originating from a leading primary vertex. This weight is used to scale down the form momentum, and it is by construction at 0 or 1 for charged particles, whereas for the neutral component, you can see the distribution of the weights on the top plots. Another technique applied by CMS uses a boosted decision tree to identify low PT jets coming from pileup. And here you can see on the left plot the contamination of pileup jets in Drellian events before we apply any discriminator. And we use this technique. With this technique, we're able to reject 95% of those noisy jets with a minimal loss in efficiency. As we heard a few talks before, at the beginning of 2017, CMS upgraded the pixel detector, extending the coverage in eta from 2.5 to 2.7. And on the right-hand side plot, I'm showing you the training in this extended coverage in eta, and you can gauge the impact on the performances before and after the upgrade. On slide number 6, we can now understand how the different algorithms perform. This plot shows the efficiency and the purity as a function of the number of pileup interactions. And as you can see inside the tracker acceptance, PAPI, that is in blue, has high performances in both efficiency and purity. But on the other hand, even though for CMS, which is in red, the efficiency is better, the purity drops quite fast towards high pileup scenarios. And to recover in purity, but at the expense of the efficiency, one can apply this pileup jet ID at different working points according to its own needs. For high eta values, we have similar scenario for efficiency, but the purity drops more rapidly in all the cases. And even though PAPI performs already better than CHS only, with the usage of this pileup ID on top of CHS, we can improve the performances with respect to PAPI only. We can also size the performances of CHS and PAPI on physical variables. For example, the jet mass resolution, which is used at the analysis level. And on the top figure, you can see the stability that against pileup brought by the PAPI algorithm. So after pileup mitigation techniques, one can cluster and calibrate the jets. And for jet calibration, CMS uses a factorized approach. And you can see here a schematic representation of this procedure, in which the first step consists of pileup subtraction. This is a simulate-based correction that aims at removing the average offset coming from pileup. And you can see in this plot as a function of eta that we monitor this average offset per pileup interaction for each type of particle flow candidate. But actually, the calibration procedure is heavily relying on the second step, which is the calibration of the jet response. Here, the main purpose is to account for discrepancies between the true and the measured energy of the jets. And if you look at the plot on the right, you can see the correction needed inside the detector from the tracker area at low eta towards the calorimeter only part at high eta. And here, changes in performances at high eta values and low PT are caused by detector acceptance. Now at this stage, the jet energy scale is well calibrated in simulation, and therefore we can apply some residual corrections to get rid of small differences between data and simulation. And we divide those corrections into two steps. There is an eta-dependent part, which is the purpose of correcting different response in each subdetector with respect to the central and better calibrated part. And those eta-dependent corrections are very small everywhere, and only in the transition region between the subdetectors are becoming sizable. And please note the scale on the y-axis. I want to emphasize that almost everywhere these corrections are less than 5%. The second part of the residual corrections have some PT dependence, and they are trying to adjust the absolute scale difference in the central region of the detector. To derive those corrections, we use a precisely calibrated reference object, as you can see here in this sketch. For example, muons, photons, and electrons, and we combine everything together into a global fit. And here you can see that the level of the correction needed is up to a few percent. Now, after that the jet energy scale has been corrected, the jet energy resolution in simulation needs to be smeared to match the resolution in data. Therefore, we apply scale factor in simulation to widen the detector response distribution. And finally, we reach fully calibrated jets with uncertainties that are less than 1% towards high PT. And as you can see, the pileup contribution is one of the most important one. Okay, so leaving jets aside for a moment, we could also talk about missing transverse energy. It arises from invisible particles, either already known as neutrinos or also new physics. And it's usually estimated from the momentum conservation in the transverse plane. This means that if we miscalibrate the visible part of our event, we will have an inaccurate description of the transverse energy. But this is not the only source of error, as you can see on those two plots. In fact, we can have anomalous high PT miss events in data that can appear, for example, from detector effects. And CMS adopts several mechanisms to suppress these spurious events in data. Now, the performances of the reconstruction of the missing transverse energy is measured in Drellian events, where we have a well-calibrated object that defines a scale and an axis. And as you can see from the sketch, we also use an hadronic recoil to balance the boson. And in those kinds of events, we do not expect any genuine PT miss. As you can see, maybe on the right-hand plot, where the mean value of the boson is, or the energy is centered down 0. Now on the left plot, we can also see the missing energy scale. And here we have a turn on, and this is due to an imperfect calibration of the lower low PT jet component of our reconstruction. And here the x-axis correspond to the boson energy scale. On the middle plot, we can also see the distribution of the resolution, which is dominated by the hadronic recoil. And we can also gauge the agreement between the three different channels that are used to perform this analysis. But also in case of PT miss, we can apply the PAPI algorithm. And it has the advantage of reducing the resolution of the missing transverse energy at the expense of having a slightly larger tails. And this is due to the wrong assignment of the neutral component in the PAPI algorithm. We can also see a direct improvement in the resolution of the transverse mass in W plus Jazz events, where we do expect genuine missing transverse energy. And here I'm presenting the same plot once for CHS and one with the PAPI algorithm applied. And you can see that the results are quite impressive. There are other features brought by the PAPI algorithm. One of those is the slightly slower turn on in the energy scale, but the big improvement is in the resolution. And in fact, PAPI show once again a better stability against pileup. And in fact, you can see that for the expected values of pileup for N3, the gain here is quite significant. Okay, so this brings me
5 minutes left.
Okay, so this brings me already to my summary, actually. I presented several techniques coming from our Run 2 experience. They already have high performances, and they will allow us to cope with the upcoming Run 3. And in this regard, the PAPI algorithm is very promising. But this is not the end of the story. We're aiming at reducing the uncertainties on calibration down to 1% for our final calibration of the Run 2 data. And for doing that, we want to increase the granularity of our correction in order to tackle the aging of our detector. In the future, also, machine learning techniques will be used to achieve even better results. So stay tuned, because more exciting results are yet to come. Okay, thank you for the attention.
Thank you. Questions to Andrea? Oh, okay, your PAPI algorithm show very good improvement for Run 2 and for Run 3, you are going to use that strategy.
That is the plan so far. We're still trying to finalize our decision, but that is the plan. PAPI will be the default one. But of course, we will also have CHS for some cases. I mean, it really depends on the kind of analysis that is being performed, that the usage of PAPI is not really suitable. So, but for the main analysis, PAPI would be the default.
Mm-hmm. Okay. Other questions? Okay, if not, thanks. And let's move to the next presentation. It's tower identification, exploiting deep learning technique. Andrea.
Yes. I should be sharing the slides. Can you see them?
Yes, we see slides and can hear you.
Perfect. Then I'll start. So, good evening. I'm Andrea. Okay, another Andrea working in CMS in Hamburg. And I will talk about the tau identification exploiting deep learning techniques. So first, here's a slide describing an overview of the various measurements that can be done with tau leptons. In particular, I'm pointing to, for instance, the measurement of the Yukawa couplings of the Higgs to fermions, or the measurement of the CV properties of the Higgs, and several also other searches for beyond standard model physics. The tau is the heaviest lepton in the standard model and has a mass of roughly 1.78 GeV. It is the only lepton that can decay both leptonically and hadronically, and it has an average lifetime of roughly 3 × 10⁻13 seconds, which means it has a decay length of roughly 1.5 millimeters, taking into account an energy of 30 GeV. Therefore, it decays before reaching the innermost layers of the detector usually. It always decays in at least one charged particle, which I will refer from now on as prong. And as we can see here, the leptonic decays always involve only one prong, while for the hadronic decays, we have usually either 1 or 3 prongs. In particular, the hadronic decays are via mesonic resonance, in particular via the raw meson at 770 MeV and the A1 meson at 1260 MeV. Regarding leptonic decays, these are usually reconstructed in Dye-Tau events, where we apply the usual selection we do in CMS. So we reconstruct a muon based on deposits also in the muon chambers in the outer part of the detector, or electron based on electromagnetic deposits in the calorimeter and tracks. And we require them to be isolated and sufficiently separated from other tau decay products. Of course, in a Dye-Tau events, we also expect the presence of missing transverse energy. From now on, I will then proceed to talk on about hadronic taus. Regarding the reconstruction in CMS, what we use is the particle flow algorithm for all reconstructed objects, which matches tracks and energy deposits in the calorimeters. For hadronic taus, there is another algorithm, which is the hadron plus strip, which assigns to particle flow candidates, which are the reconstructed objects from the particle flow algorithm, to a hadron, which would come from the decaying tau, and particle flow candidates associated to an electromagnetic shower in the electromagnetic calorimeter to a strip when they are elongated in the phi direction of the detector, because that would be a signature of the decay of a pi zero. Originally, this HPS algorithm had 3 decay channels reconstructed, which are the 3 ones I'm pointing here, while in the latest version, we have 4, which are the 1-prong plus pi zero, 3-prong, and 3-prong plus pi zero. There are several objects that can be misidentified as hadronic taus by this algorithm. And in particular, there are jets. In particular, if a jet is highly collimated, it can mimic pretty much any tau decay. Then we have muons, which usually contribute to a contamination for the 1-prong decay. And electrons, for which I am pointing out here a brief sketch. In particular, an electron can have sufficient energy to reach also, in terms of a shower, also the hadronic calorimeter, and can be misidentified as a hadron as a result. And it can emit photons via Bremsstrahlung radiation, which could be misidentified as the decay of a pi zero and therefore as a strip. The result is that the electron pretty much can mimic the decay of a raw meson. To reduce the misidentification rate, a neural network-based algorithm was introduced, and it's the deep tau algorithm. This algorithm is based on a convolutional neural network, and I will proceed now to describe first the inputs of such a neural network. In particular, we have low-level inputs based on the tracks and energy deposit of particle flow candidates, and high-level inputs which are related to the properties of the tau candidate and some general event properties. I'll then move on to describe the general structure of the neural network, and then proceed to describe what we do with the outputs. We have 4 output nodes, in particular 1 for the genuine taus, and 1 for each misidentifiable object, so jet, electron, and muon. And from these 4 output scores, we retrieve 3 classifiers, taken as the ratio of the score for the tau divided by the score for the tau plus the score for the other object. So this classifier will be close to 1 if the object is very likely to be a tau, and very small if it's very likely to be a misidentified object. In terms of input features, we divide them, as I said, in low level and high level. The low levels are constructed in the following way. We divide the CMS detector in cells of eta times phi, and in each cell, we take all available information for the leading particle flow candidate, so the one with the highest energy. We also have a higher density of cells in a signal region, which is defined with respect to the direction of flight of the leading tau decay product of size that are 0.1, and an isolation region of size 0.5 that are size 0.5 constructed around it. The idea of having 2 different granularities is that this allows to have a good compromise between having a high number of features for the neural network to be able to reconstruct correctly which object decayed or which signature has been found in the detector, and a low enough number of features so that the computation time and memory-wise use of the neural network is reasonable. At the moment, we have 180 up to 188 features per cell. We also have 47 high-level inputs, which are the properties of the tau candidate, for instance, the PT, eta, phi, HPSDK mode, and so on. And other properties, for instance, the average energy in the event, and the eta separation between the direction of flight of the tau and the leading photon or electron in the strip, for instance. In terms of structure, this is a convolutional neural network, which takes as input something of the order of 100,000 low and high level features, and says something of the order of 1.5 million trainable parameters. Regarding the low-level features, these are pre-processed to reduce the number of features. There are 3 convolutional layers associated to the various substructures in terms of features, so for electron, photons, and hadrons. And then they are processed through other convolutional layers with window size 3×3 to concatenate the various features between the different objects. High-level features are pre-processed via directly dense layers, and then all the various features from the different sources are merged together and processed via 5 dense layers, leading up to 4 output nodes. The training is performed using the N-Adam algorithm, and due to a number of parameters, we run the training on 1 GPU, and it takes roughly 3 days per epoch. Here, I'm now showing directly the classifiers that we obtain from the output nodes, particularly the against muon classifier and against electron. In this plot, I'm showing the misidentification probability on the y-axis and the efficiency in the identification of genuine taus on the x-axis. Here, I'm showing not only the classifiers obtained with the deep tau algorithm, but also the previous classifiers used in CMS. In particular, we had a cut-based one for the muons and an MVA-based one for electrons. And we can see that the use of the deep tau algorithm, so of the use of deep learning, improved, reduced the misidentification rate. Regarding JET, we have 1 classifier, as I said earlier. However, to estimate the misidentification rate, this is done in 2 separate studies. In particular, we look at the jets coming from TT-bar events and jets coming from delta jets events. And here I'm showing the updated deep tau classifier and as a comparison, the former MVA-based one. And we can see that we have overall a nice increase in the purity of the selected taus. Moving on to analysis level, I'm showing here the visible mass distribution on the left using the old MVA discriminators, and on the right using the new deep tau identification. We can see from the increase in this yellow histogram, which is the Z2 process, that we are increasing the number of collected genuine taus, and this is done by a factor of 20%. While from the decrease of this red, pink, and blue histograms, which corresponds to delta jets, QCD multijet, and ZLL, we are reducing the number of fakes, comparing left to right. And this is done by roughly 23% as cumulative among all the different types of fakes. To conclude, I showed today the tau identification exploiting deep learning techniques, which has noticeably reduced the misidentification rate and increased the fraction of collecting genuinely adjoint taus. We also have increased the possibility to model Monte Carlo to data correctly, and we have correction scale factors that are now of the order of 10%. There have been, in parallel, performed other algorithms in CMS. In particular, we have a detector performance summary here regarding a low PT tau identification algorithm, which is focusing on specific kinematics, and in particular, this one on the three-prong decay channel. At analysis level, there have been several new analyses which obtained a noticeable gain by using the deep tau identification. And tomorrow there will be an overview shown at the Higgs session at 9:30 by the title Higgs boson measurements in final states with taus at CMS. So let's look forward to the new physics result with tau leptons. Thanks.
Okay. questions to Andrea? Okay, I would like to ask questions. You show that your deep learning technique allows to improve efficiency and decrease fake rate essentially. The number of, do you have some room for improvement, for example, by increasing number input parameters, or it's already saturated?
We have still some room for improvement, and there are plans for essentially phase 2 upgrades to have a new version of the architecture to try to optimize further the fake rejection and the efficiency in the section of taus. One thing, for instance, that we are currently improving on is also combining this deep learning technique, also, for instance, to recognize the decay modes of the taus on top of this HPS algorithm I talked about. So there is still room for improvement, and there are plans currently in motion.
Okay, thank you. Other questions? Okay, if not, let's thank speaker and let's move to another presentation, UJET tagging technique at CMS by Dennis Schwartz.
Yes, hi everyone. Let me share the screen. Okay, perfect. Can you hear me well and can you see the slides?
Yes, we can see your slides and can hear you. Please go ahead.
Oh, okay, perfect. Yes, so hi everyone, my name is Dennis and I'm going to talk about new jet tagging techniques at CMS. And as you all know, at the LHC, we have abundant jet production, and these jets can have manifold origins. So jets can originate from light and heavy quark flavors. There will be actually a talk focusing on this. So basically focusing on B-tagging and the discrimination power against light jets and gluon jets. I think it's actually the next talk. Then you already heard from Andrea the identification of jets that originate from pile-up vertices. And so this makes it possible for me to focus on the last source that I listed here, and these are boosted heavy objects such as top, W, Z, or Higgs bosons, which I will cover in this talk. Okay, so why do we care about boosted heavy objects? A typical example would be a search for new heavy particles that then decay into these heavy objects, so top, W, Z, and Higgs. And when these particles are heavy, then the decay products have high transverse momentum typically. And this leads to the fact that we have boosted decays. So we cannot reconstruct the decay products of a top, for example, as separate jets, but all decay products merge into a single jet. And this is sketched here on the bottom, where we have, in case of a top quark that is produced at rest, we have 3 separate jets in the hadronic decay, and they all merge into one large jet in the boosted case. So how can we identify those jets? And the answer is we use jet substructure, so basically properties of the jets. And two common examples is using the n-prong structure of a jet. So there we make use of energy distribution functions. I guess the most prominent example is the n sub jettiness, where usually the ratio, so tau2 over tau1 or tau3 over tau2 is used. And as an example, you see the plot on the right, the top plot, where you can see the 2-prong decays of the W, Z, and Higgs against the 1-prong decay of QCD. And you can nicely see that all these bosons accumulate at low values of the tau2-1, and this can be used to identify those jets. Another prominent example is the jet mass. Since the jet mass should be sensitive to the original particle's mass. And this is exactly what you can see on the bottom right plot, where we have these nice peaks of all the bosons at their corresponding masses, while in QCD, we have a falling spectrum starting or peaking at very low values. So typically we can use those, those observables to distinguish jets and identify them. But the question is, can we do better? And obviously the answer is yes. And first example that I would like to show is the boosted event shape tagger, which is called BEST. And here the idea is that you boost your decay back into the rest frame of the original particle by assuming a top W, Z, and Higgs mass. And if you catch up the correct boost, then your decay should lead to an isotropic angular distribution. And also you should be able to see some momentum symmetry in this rest frame. And this momentum symmetry, or better, the momentum asymmetry, is displayed in the plot on the right side, where, for example, when you boost, assuming the W mass on the top row of the plots, then you have an asymmetry which is distributed around 0 for W jets, and for all the other jets you have some other values. And the same also works for the top, as the bottom plot shows. And these features, so the information that you can gain from boosting into the rest frame of the original particles, is then combined with additional jet properties, for example, the end subjettiness or the jet mass in a fully connected neural network. And this can be used then to identify those heavy objects. But you can go even further and include even more information about the jet. And this is done, for example, in the deep AK8 algorithm. And this is also a multi-class classifier. So you can distinguish tops and also Ws and Zs and so on. And this is a machine learning approach that makes use of all the particle candidates. So what you actually plug into your network, into your neural network, is properties of up to 100 jet constituents, and also properties of up to 7 secondary vertices. And this is an enormous amount of information. So you need this neural network structure to really learn something from this. And you start with actually 2 separate networks, so one for the jet constituents and one for the secondary vertices, and extract features with a neural network. And then these features of the 2 inputs are then later combined with a fully connected layer. So the architecture is sketched there on the top. Yes. And on the bottom, you see the discriminator, so the output of this network for the mode where you want to identify top quarks. And it's very nice to see that actually after all this network, we still have a nice data to Monte Carlo agreement in this discriminator value. One thing that Deep AK8 also learns is the jet mass. So you plug in all the jet constituents, but Deep AK8 is able to learn the jet mass. And this also means that it sculpts the MJet distribution in the end, which you can see on the right plot, where the Deep AK8 in blue really has a shape of a W peak for all jets that pass this requirement. And this makes it difficult for some analyses, because you cannot even see resonances on top of your background anymore, because your background distribution is sculpted weirdly. And in CMS, we have many decorrelation approaches. I can just show you one here. This is a mass predictor network. So you basically have a second network that tries to predict the jet mass of the jet. And then you can assign a penalty to your original classifier network if your output is largely correlated with the mass. And with this, you achieve basically a smooth background distribution after the decorrelation, which is shown in the same plot here in the green dotted line, which is then the nice spectrum you would assume from QCD. In CMS, we have then a large machinery that validates all these taggers and all these performances. And you can see ROC curves for all different taggers. This is also for the top example on the top right, so top versus QCD. And what you can see is that all the machine learning taggers already outperform the classical taggers. So this is really nice to see that Deep AK8 here in blue has the largest signal efficiency for the same background efficiency as other taggers. So this really helps in the JET tagging, the neural network approach. And then we derive correction factors for all these taggers in order to be able to correct for different efficiencies in data and simulation. And you see some examples on the bottom. And it's very nice to see that basically all the correction factors that we extract are compatible with one or let's say close to one, almost over all range of taggers, and this is very nice to see. One new example that I would like to show is ParticleNet, and ParticleNet is also a tagger, and ParticleNet has actually the same inputs as the Deep AK8 algorithm, but has a very different architecture. So ParticleNet is a so-called graph neural network. And what you basically learn, or what the network tries to do, is to find two particle correlations, so correlations between particles. And this is somehow sketched on the right, where you can see decays of the top plot is from a light quark jet, and the bottom plot is from a W jet. So you can already see the one prong or two prong decays here, and these lines that represent basically correlations between all these particles that are the squares and the circles that you can see in these planes. And really just from changing the architecture of the network and not changing the inputs, you can already gain. So in the performance plot on the bottom left, you see a comparison between the Deep AK8 and the ParticleNet. And in this particular phase space that is shown here, this is again the top quark identification. The ParticleNet outperforms the Deep AK8 algorithm. So it's not only about including more and more information, but it's also really about creating an architecture that can make use of all this information. And this brings me to my summary. So I hope I could show you that jet identification is crucial for most of LHC analyses. And at CMS, we have a large machinery which validates the performance of all these taggers. And as I've shown you, the categorization of jets, or the identification of jets, already largely profits from machine learning techniques. And there are lots of new taggers that are developed, and they are developed to even better performance. And there's even more taggers that I didn't have time to show you. So there's ImageTop, which basically projects also the decay or all the particles in a jet on a plane and plugs this into a neural network. And there are classical cut-based taggers such as the CMS top tagger or the HotVR tagger. And yeah, there's much more to read about, and much more to come, I guess, in new taggers. Thank you.
Okay, thank you. Questions to Dennis?
Maybe I would ask, these are of course fantastic applications of neural networks. The question is, are you all, for the training of these networks, are you using purely like Monte Carlo or some mix with data, or how is it?
So I think for most of the taggers, this is for now purely simulation based, the training.
Okay, and yeah. Okay, thanks.
Okay, other questions?
Yeah, maybe one more question are these when the network is trained, is it possible to use it somehow online, or it is always for the offline analysis?
So I only know of the use for the offline analysis for all these taggers. I cannot really think of somewhere where you can use them online.
There is no way how to use it, for example, in the trigger.
You mean directly for example, top tagging?
Yeah, you would be selecting online something using this.
So I mean, I guess it should be possible, but I'm not an expert how this works out in performance and if this is quick enough. So I guess it's not quick enough when you use all these constituents because you don't have them at trigger level.
Okay, thanks.
Okay, thank you. So let's move to the last presentation of this session, heavy flare tagging in CMS in round 2. Alessandro.
Hello, can you see the slides? And can you hear me?
We can hear you, but cannot see your slides yet.
Can you see them now?
Yes.
Perfect. So I'll be discussing about heavy flavor tagging in CMS round 2. So first, a quick outline of the talk. Of course, jet flavor identification and calibrations are quite crucial when it comes to all the major physics analysis at HC for Higgs standard model, BSM physics, and so forth. The big quarks are present in a top quark decay, so of course they are of paramount importance for such analysis. And also in the case of the Higgs, of course, this is just an example, but the largest Higgs decay branching ratio at 125 GeV is in BB bar. So of course, we need to achieve a very good tagging performance there. So this slide is mostly outlining the talk. I'll be giving a very quick introduction of the CMS heavy flavor tagging, defining the main features, then algorithm performance, as well as results for boosted and resolved jets, so the ones which are reconstructed with a large cone or rather a small cone, depending on the kinematics of the final state. Then a little bit more in terms of highlights and application of CMS physics measurements, where B-tagging is being used extensively to improve results, and also CMS upgrade projects. A little bit more on calibration techniques, the one that actually equalize the efficiency response in simulation with respect to data, and finally wrapping up and conclusions. So just to start off, we see this very nice event display where CMS collision is depicted with 3 jets, which are reconstructed in 3 AK4 techniques, and as well as a multitude of tracks, as well as reconstructed primary and secondary vertices. So let's start off with heavy flavor tagging. Of course, B jets stem from the process of hadronization of B quarks, and we can make use of the properties of B hadrons to identify such B jets, mostly the mass, also the long lifetime that actually creates displaced tracks and secondary vertices, the large momentum that is being carried by B hadron, which is around 75% of the full momentum, and also the presence of direct and indirect semi-atomic decays coming from the fact that the B can decay into leptons, or through C with branching ratio of around 12%. Now, the general strategy in CMS and also in general high energy physics experiment is to make use of inputs from low-level taggers, which actually exploit the full feature of the final state and the B-jet decay topology, such as, for instance, the impact parameter of the tracks associated to the jets, also the presence and the shape of the distributions associated to secondary vertices and so forth. And then we combine the information on such low-level inputs in high-level observables, which are being fed into deep neural networks or boosted decision tree algorithms. So one important feature I'd like to mention here is that actually in CMS over the past couple of years or so, there has been a very strong push for developments of deep neural network-based techniques, which actually overperform quite dramatically the previous results. So let's start off with the first discussion on the tagging inputs for the resolved jets. In this case, as I said, we make use of features which would separate between the light flavored information with respect to C and B jets, for instance, the track impact parameters, the secondary vertex features such as the mass, the flight distance, and so forth. Here you have, for instance, some of the example plots where you see the various contributions of light C and B components in blue, green, and red respectively, and how they behave with respect to data as a function of the input variable. You see that the modeling is pretty nice throughout the full spectrum. And then, as I said, we make use of deep neural network algorithms, in this case, the so-called deep CSV in CMS, that is trained on multi-jet events and also on top quark pair events. And actually, they make use of such input features to get a high-level variable. You see the deep CSV discriminator here in the bottom part of this slide, which provides the B versus light and the B versus C separation. This is then being used, of course, in physics analysis by exploiting a selection on such a variable, which tags the jet with a given efficiency. Another important feature here I'd like to mention is that not only do we need to account for B tagging, but also for C tagging, right? So C tagging is an additional challenge because, as you see from here, the very well-known plot of the impact parameter, 3D impact parameter significance of tracks associated to B, C, and light. The C component is somewhat between the B, which is of course featured by the very large tail due to the lifetime component, and the light part. Therefore, the C discrimination is made possible on top of the B1 by exploiting the same deep CSV algorithm with two additional output nodes for light and for B discrimination. So let's move on a little bit further. As I said, we've tried to push towards improvement in technology to account for better tagging. So before we made use of input features, high-level input features in deep CSV, but then in order to get more performant taggers for the final run 2 legacy results in CMS, we also developed a DeepJet, which is actually to be considered as a sort of successor of deep CSV. And as I said, it makes use of low-level input features, unlike the previous algorithm, from particle flow candidates. So these actually, most notably, the properties of charge and neutral particles, which are associated to the final state, as well as secondary vertices. And as you see from the ROC curve here, we see that for a given BJet efficiency point, if we compare the performance in terms of mis-ID probability for DeepJet and deep CSV, which was the old version of the tagging algorithm, there is a significant performance gain. This mostly comes from the larger set of low-level inputs, which also account for correlations among such inputs inside the network, and also by the fact that we make use of a less restrictive track selection and a more suitable, as I said, complex neural network architecture. Here you have links to presentations and public results from CMS where additional details are provided. So let's move on a little bit further. We've discussed about resolved jets, and now let's turn to boosted jets. That has, as already mentioned in a very nice presentation that just came before mine, there are several measurements exploring the high PT regime in order to mitigate the overwhelming QCD background, which is of course the main, the one that is actually playing a role in most of the physics analysis there. So in CMS, the collimated B jets are reconstructed using 0.8 cone jets. And as I said, we do exploit boosted taggers in several physics measurements, mostly for two cases, the so-called deep double B and deep AKH. You see here the distributions of the results for such taggers as a function of the usual signal efficiency. In these two cases, we feed the network using boosted features provided, and the network itself actually provides distinct probabilities for the BB signal component versus the light flavor versus the top and versus the QCD background. And of course, depending on the analysis and on the dominant background, we can choose the most suitable output node. So as already mentioned before, we did experience a very large gain with respect to previous algorithms. And as you see from the plot here, when we compare the red with respect to the blue line, which were based on a kind of simpler architecture. And also we've managed to successfully mass decorrelate the output, as already mentioned in the previous presentation. A little bit more on the highlights on B-tagging physics analysis and upgrades before moving to the second part of the presentation. As I said, several CMS physics measurements have benefited dramatically from the improved B-tagging performance. Here I've just mentioned two within the Higgs realm. So the Higgs to BB 5 sigma discovery that was achieved a couple of years ago. Here you have a link, and also the inclusive high PT GG Higgs to BB search. Again, more links to presentations and to talks later on in the sessions, where B-tagging is playing a leading role. This is not only for say run 2 analysis, but also for upgrade. In CMS, we've recently released a technical design report on mid-timing detector, in which we improve quite a bit the B-tagging characterization by increasing the overall performance, accounting for timing information associated to the track selection. Here you have the output, the results in terms of probability as a function of BJet efficiency for different pileup profiles. And you see that we do not lose that much of a performance, even if very high pileup, 200, the one that we expect for Halum Elite C, if we introduce a timing selection at the tracking level, and then if we run B-tagging. So let's move on to the second part of the presentation, calibration on data. So the technique actually will have to be validated on data in order to ensure that the performance, namely the efficiency of very flavor tagging in simulation is the same as the one in data. For that, we exploit several topologies and final state, which are typically enriched in B, C, and light flavor jets. For B jets, we exploit TT-bar events and events where we enriched in muons from semi-leptonic decays. For C, we exploit a W+C component, and for light flavor jet, we make use of QCD multi-jet events in which we extract the light flavor jets. One important feature to mention is that the majority of calibration methods, they calculate scale factors, so the data MC efficiency ratios for fixed cut on the discriminator value. So we have a shape, and then we define a given efficiency up to which we calibrate. However, in some specific cases, we also fully calibrate the shape of the algorithm. This is most notably the case for deep CSV and deep jet, which is quite useful for physics analysis, such as, for instance, the Higgs measurements in the BB final state, which actually make use of the shape and not just the fixed cut operating point. Another important feature is that, as you see from the plot here in the bottom part of this slide, we have a full set of calibration methods and sometimes more than one option for a given method in order to ensure redundancy on the outputs and also to exploit the combination of the results. Here, for instance, it's the case of the B calibration, where you see that the various methods do agree quite nicely as a function of one of the jet kinematics we calibrate against, which is the PT of the jet. So let's quickly go through the calibration techniques. First, B jets. In this case, as I said, there are two main methods. One, which is based on semi-leptonic and dilepton TT-bar events, where we probe we tag one jet and then we probe the other one to determine the efficiency, or we try to remove as much as possible the component from ISR and FSR jets, which is our background for the analysis, by exploiting a BDT with kinematic variables. This is the case of the kinematic fit for the TT-bar calibration. And then another very reliable method is based on the presence of muon in the final state. And as you see from the bottom here, the plot here in the bottom part of this slide, the PT-rel information, namely the PT of the muon with respect to the jet axis, is actually quite discriminating in the case of B jet here in red with respect to the light and C option. And this is actually being used to enrich in this specific flavor, named B, and extract the calibration factors. For C jets, this is a bit different because in this case, we exploit the W+C topology. And in this case, W and C are opposite sign, whereas the background, which is W plus generic QQ bar pair, is actually a balanced opposite sign, same sign. Therefore, by exploiting this opposite sign minus same sign technique, we can fully enrich the sample in W+C with a signal purity, which is quite large. It's around 60 or 80%, depending on the flavor of the lepton. And from there on, we extract efficiency in data in Monte Carlo to get the scale factors as a function of the observable. Another method, as you see from the plot here in the bottom part of this slide, is making use of TT-bar semi-leptonic events in which we again enrich in C-jet with a dedicated kinematic reconstruction. However, this is actually quite limited, as you see from the plot here, by the statistics of the sample itself, but still it enters the combination with the main W+C method, which drives of course the measurement. One more.
You have 1 minute left.
Okay, thanks. Just the last one. One more point related to the light flavored jets. In this case, as you see, the scale factors themselves in the bottom plot are quite larger with respect to the one we extracted from C and B. And also the mismodeling, which actually creates the up and down variation, is around 5–10%, as you see from the systematics band around the central value, mostly dominated by the mismeasured trucks. And here we make use of the fact that the distribution should be symmetric for light flavored jets in the main observables, especially, for instance, the impact parameter, and then the non-zero value of such impact parameters can only come from resolution effects. So I'll be quickly going through the last slide, which just brings me to my conclusion. I hope I've conveyed the idea that actually heavy flavor tagging is a crucial ingredient for all physics measurements and searches at LHC. I've presented a quick overview of the algorithm developments for B, C, and light mistag identification. Several new algorithms are being deployed. We have a an excellent background discrimination level, and this has definitely paid off, both in terms of searches as well as measurements and upgrade projects where we make use of B tagging, such as the CMS flagship analysis using, for instance, VHBB or TTHBB, where B tagging is playing a leading role again. And when it comes to calibration, the B and C tagging algorithms are also checked against data efficiency. The calibration analyses are actually very complex measurements and have largely benefited from a combination of such results by using several methods targeting different phase spaces in order to ensure combinations and redundancy. Thanks.
Okay, thank you. Questions to Alessandro? So about calibration, what's the accuracy of calibration do you have?
So this is actually very flavor dependent, as I said. So for B calibration, as you see from this plot, the accuracy is very nice. It's less than 2–3%, and also it's a bit, dependent on the PT bin we are talking about, and this is a bit less accurate in the case of the light flavor calibration. You see that the band around the central value is around 5–10%, and this is mostly because of the modeling of trucks, which is the main bottleneck for this analysis.
Okay, thank you. Other questions? Okay, if not, thank you, and thanks to all speakers of the session. So we a little bit behind of schedule, so let's have 5 minutes coffee break, and we will resume at 7.
I think that we can put 7:20 easily.
7:20 and
7:20.
Jury will chair the next session.
Yes, thank you very much, Alex. Very good work, and thank you to all the speakers for very nice presentations. Of course, it is very technical now, but still we have 7 talks. So let's start at 7:20. I'll be back in like 3 minutes, and we can try also some sharing, or you can also try with the ZTA with Tadeusz. So please check if you are able to share, so we will have a smooth rest of the session. Thanks.
Hello, just testing my connection. Can you hear me?
Yeah, do you hear me?
Yeah, perfect. I might just check slide upload as well.
Cool.
Working fine.
Okay, awesome, thanks.
Yes.
Do you see the slides?
Yes, perfect.
Okay, thanks.
Can you see my slides?
Yes.
Also,
Nice.
now that on?
Yes, they are changing.
Okay.
Looks good. Okay, when I'm checking the speakers, if they are present, I am not able to see Benjamin Taylor. Okay, hopefully he will be able to join. Okay, I think that in principle we can start. So
please wait a minute, just a couple of seconds. I'll start the stream.
Okay. Okay, I can see you started recording.
You can go ahead.
Okay, perfect. So this is the last part of this session, the second session of the track 12, and we will start with Victor with flexible physics selections at 30 megahertz. So Victor, if you can start, share.
Okay. Do you see the slides?
Yeah, perfect.
So you hear me well. So my name is Victor, and on behalf of the ICHEP collaboration, that's my pleasure to discuss flexible physics selections at 30 megahertz. First thing first, I have to introduce the ICHEP trigger in 11112. And the first thing I want to say is that for general purpose LHC experiments, the signatures were roughly in the kilohertz region in terms of rate. So a readout at 100 kilohertz was extremely efficient. And LHCb, which was designed to study beauty and charm physics, had a rate of dB bar around 45 kilohertz and a charm CC bar rate of roughly 1 megahertz. So 1 megahertz readout was a requirement. And the LHCb trigger had to be flexible enough to give high efficiency for rare decays such as B2K star mu, as well as high purity for child physics with here D2K pi. So the strategy in run 1 and run 2 was to have first a hardware trigger, the L0, followed by 2 stages of software trigger, HLT1 and HLT2. In upgrade conditions, we have 5 times the luminosity available during run 1 or run 2. For general purpose LHC experiments, there is no major change in the trigger strategy. But for LHCb, the signal rates will be up to a few 10 megahertz. So having a hardware trigger is actually not possible anymore, and the L0 trigger will be removed. And such high signal rates also change the purpose of a trigger. We go from rejecting backgrounds to categorizing different signal modes. So this is the scheme for the HB trigger in run 3. A full software trigger with first with 2 layers, HLT1, which will be run on GPUs, which has to deal with the detector readout at 30 megahertz, which is the frequency of colliding bunches in the LHC. Track reconstruction of charged particles and selections based on single and 2 tracks. A buffer in between HLT1 and HLT2, and HLT2 dealing with a full reconstruction, the detector alignment and calibration, particle identification, and at least 1,000 selections to deal with. To compare with run 2, we have 5 times the luminosity, 30 times higher HLT1 input rate, and the disk buffer is reduced from a couple of weeks to a couple of days. So this trigger has a number of challenges to answer. First, an efficient HLT1 reconstruction at 30 megahertz that will be discussed by Renato during next talk. A real-time alignment and calibration procedure which gives offline quality, and Maria will discuss this on Friday. And of course, selections that I will discuss in this talk. So in addition to having to be really fast, 1,000 selections to deal with gives a very complex graph, and the execution itself has to be optimized. So the trigger selection framework was revisited. It consists in the data flow, which are configurable algorithm properties, and inputs and outputs defined by users that create selections, and a control flow, which is what should be run and when to stop. Here on the right, you can see a mock-up of a trigger line, which is based on 2 sub-lines. So the decision and line 1 and line 2 are composite nodes, which means that they can be associated with logic and or not, and that there is a possibility to execute all children of a composite node, but you can also allow for a short circuiting if at least one of the children gives a positive trigger candidate. And at the bottom here, you see basic nodes, which are only one algorithm plus a list of its data dependencies. And here you can have a prefactor, a prescale, a global event cut, and a filter. So for the execution, the data dependency is constructed by matching input and outputs of the different basic nodes. And these basic nodes are then reordered to respect the data constraints. So you go from a slightly complex graph to a single list of ordered algorithm to be executed. And here is an example of a more realistic trigger selection with algorithms in red, the control flow, and the different objects that pass through in blue. So you go from objects to slightly more elaborated objects to a final decision on your selection. Renato will discuss more the HLT1 itself, but you want to have a quick look on its really good performances. You can see here the track reconstruction efficiency for tracks coming from BDKs as a function of transverse momentum. And here you can see the muon identification efficiency as a function of momentum. And here are the different lines that are run at the HLT1 level. So one track, two track selection, as well as time muons and dedicated charm trigger lines. And here is the total HLT1 output rate currently. So as I said, HLT2 level has to deal with a really high number of lines, both inclusive and exclusive. So sharing the fixed 10 gigabytes bandwidth, output bandwidth, will be challenging. And this can be optimized using a genetic algorithm where both rate and efficiencies are taken into account. And there is another layer of flexibility, which is the data output, which can be defined by the user, because a trade-off can be achieved between selection rate and even size using turbo. So as rate is no longer relevant and output bandwidth is the major constraint of the HGB trigger in run 3, turbo is the LHCb framework to create reduced event format data. In the most extreme case, all raw event is dropped and only reconstructed objects used to create the trigger candidates are saved, which gives an average event size of 15 kilobytes. And it can go all the way up to dropping raw events, but saving all reconstructed objects, which gives 70 kilobytes. And each user designing a selection can define a selective persistency where some parts of the event that can be meaningful for future physics analysis can be saved. And here at the bottom, you see the full reconstructed event being saved up to only the trigger candidate being saved, and everything in between is possible on a case-by-case basis. And turbo has already been proven during run 2. There's also an ongoing effort on improving HLT2 performances. Efforts were concentrated on HLT1 first, but are now shifting towards HLT2. And here is the current breakdown of the throughput for the HLT2 reconstruction. Run 2 selections are currently being ported to the new framework with positive feedbacks from users. And the integration of the HLT2 with HLT1 being run on GPUs is also ongoing. So to conclude, the LHCb trigger in run 3 will have high rates, meaning that we go from rejecting backgrounds to selecting signals. And from optimizing rate to optimizing bandwidth, it will be a full software trigger with a detector readout at 30 megahertz, HLT1 on GPUs at 1 megahertz, and HLT2 on CPUs with fixed bandwidth of 10 gigabytes per second. And flexible selection will be achieved with a framework to reorder algorithm based on user-defined inputs and outputs, and a reduced event format for storage with flexible user settings. Current developments are primarily targeting improving HLT2 performances, bringing new selections to problem-free, and preparing for commissioning. So thank you for your attention.
Thank you very much. Very nice presentation. Questions? Are there any questions? Nothing on Mattermost. Actually, I would have a question. Actually, what is exactly the reason why using the GPUs for the first level and the CPUs for the second? It is just the speed, or?
So it's a mixture of performances and physics performances. The HLT1 on GPUs has proven to be cost-effective and being able to give better physics performances. But for HLT2, as we have a buffer, we have more time to process, and HLT2 on GPUs won't be cost-effective, I think.
Okay. And the second question, what is actually limiting the bandwidth?
Storage, how many disks we can buy.
Okay. So no problem with cables or something like this, just the storage.
Yes, this is definitely the major constraint.
Okay, thank you. Any other questions or comments? If not, thank you very much again. And we will move to the second presentation, which is Renato.
Yeah, can you hear me?
Yes. You can try to share.
Yes. Can you see my slide?
Yeah, perfect. Yes.
Do you see the first one?
Yes.
Okay, so hi everybody. Today I'm going to talk about the physics and the throughput performance of the real-time reconstruction at the LACB upgrade. So the LACB detector, as briefly introduced by Victor, it's an high-precision experiment at LAC optimized for BNC hadron decays. Here it's a sketch with the various sub-detectors, highlighting the detectors responsible of tracking and the ones responsible of particle identification for charged particles final states. It has shown excellent performance in run 1 and run 2, and more details can be found in the talk from Martina. And the detector is designed as a forward arm spectrometer because in proton-proton collision, the BB bar and CC bar are produced boosted in the forward region. Now, apart from the sub-detector's performance, it's important that you take decisions and select events in an efficient way. And here it's a sketch of the trigger schemes and how it has evolved during run 1 and run 2, and how it will look like in run 3. As Victor said, the run 1 and run 2 has been characterized by the presence of an hardware trigger, which were aiming to reduce the 40 megahertz input rate from the proton-proton collision to a 1 megahertz event rate, which was the limitation of the readout of the whole detectors, the tracking system, for example. And this 1 megahertz input rate were then passed to a software trigger split in 2 steps, one aiming to further reduce the rate from 1 to 100 kilohertz and performing just a partial reconstruction of the events, taking some selections and then going to the second stage. And during run 1, the output of the trigger was expressed in kilohertz, meaning in events per second, and the reconstruction was performed again offline, with alignment and calibration constants updated. In run 2, this has changed with the real-time alignment and calibration paradigm, which consists in having this intermediate buffer perform the alignment and calibration, have offline quality information directly in the online system, and perform analysis directly from the trigger, which triggers directly to what is going to happen in run 3, where the hardware trigger will be completely removed, and the full non-empty bunch crossing rate will be reconstructed at collision time, basically with a 30 megahertz input rate. The event rate will be reduced by the partial event reconstruction from HLT1 to 1 megahertz, again with the buffer, and then you run HLT2 and the selections that Victor presented, which converts the output rate from kilohertz to gigabit per second, because as Victor explained, you start to optimize the final bandwidth and not anymore the event rate. Now, all this change in run 3 impose that you must be able to read out the wall detector at 40 megahertz. And the main reason behind this is that the LACB in run 3 expects to operate at 5 times higher instantaneous luminosity, which means that for each single collision, almost 1 out of 3 of them will have a CC bar or a DB bar hadron, which shifts the trigger paradigm from rejecting background to categorizing signal, basically. And moreover, you have much more TVs, more tracks, and more signals, which comes back a bit to the basics. How can you actually trigger in LACB an event which is from a B or from a C hadron? What are the kind of informations you need? So if a particle comes from a B or a C hadron, it has a transverse momentum at the order of GV, at least in one of the final states. Then those tracks originate displaced from any primary vertex, and you can identify for a single track how it is displaced from a single primary vertex, or when you combine more than one track, you can find some secondary vertices and evaluate how displaced it is. The challenge in run 3 is exactly this: be able to find those PVs and tracks and find the momentum and transverse momentum of them, and possibly identify also the type of track, for example, if it's a muon or not, in real time, so directly at 30 megahertz input rate. So you need to perform this track reconstruction at collision rate, which is a huge computing challenge. And this huge computing challenge in LACB has been tried to be solved in 2 different approaches, which landed in 2 different TDRs. One using CPUs, where the HLT1 reconstruction was executed in the server farm after shipping the 30 megahertz input rate from the event builder. And the other approach, which is what is going under the name of Allen project, is to do that on GPUs, where you plug the GPU cards directly on the servers available in the event builder. You run the reconstruction, you take selections, and you ship out a 1 megahertz output to the server farm, which performs the full event reconstruction and selection and storage to disk. The final decision taken by the LACB experiment is to use GPUs for the HLT1, and one of the major benefits of doing that, apart of being cost effective, is that it allows to reduce the network bandwidth between the event builder and the server farm, and as well free up the filter farm to perform the full event reconstruction on CPUs. Now, what does it mean, this HLT1 reconstruction? What are the tasks that has been implemented that are fulfilling the requirements of the LACB upgrade? So here it's a brief scheme of how it will work. So you have the servers in the event builder, which will ship the raw data to the GPUs, which will decode and prepare the data and the value sub-detector to use the reconstruction, perform reconstruction, make decisions, and then the events that you select will be sent to the filter farm. Now, the HLT1 is composed by various small algorithms, which are composed by data preparation in various sub-detectors, in particular the tracking sub-detectors and the muon system, and reconstruction in the various sub-detector, and I will describe later the reconstruction sequence that is executed. And at the end, it takes selections based on information of 1 track or 2 tracks. Now, LACB has developed all of this on GPUs, and when you deal with that, you need to know how to actually parallelize on GPUs, and the scheme that has been followed is to pipeline many HLT1 reconstruction sequence across thousands of events in parallel for each GPU cards, and within each event, you parallelize the single algorithm. So depending on the task, you typically parallelize in different way. Just as an example, for raw data decoding in the various subdetector, you parallelize not only across the events, but also across the readout units. While for track reconstruction, for example, in pattern recognition, you want to assign or add hits to a given track candidate, so you can parallelize across the combinations of hits that you're building along the way. And if you have a seed tracks, you can parallelize as well across the seed tracks that you're dealing with. Now, the first algorithm that runs on this reconstruction is the velo tracking, which use the vertex locator for the upgrade. The detector is placed close to the interaction point, so you have all the kind of tracks which comes out from proton-proton collision. And typically in this region, you have basically you have no magnetic field, which means that all tracks behaves as straight lines in the bending and non-bending plane. And this implies that all tracks are more or less all contained within a given phi azimuthal angle region. The way in which this has been implemented and parallelized for GPUs is to interleave steps, one called seeding, where you iterate over all possible 3-hit combination from 3 consecutive modules from the velo, and you build all those combinations in parallel, and then you forward them to the next module, and given the alignment in phi, you basically maximize and optimize the data structure such that those hits will be exposed for maximally to get the fastest algorithm as possible, benefiting from the spatial and temporary locality of that. And then you interleave this with another seeding step and forward. Now you have segments in the velo, and you propagate them to the upstream tracker, which is the tracker which is placed upstream the dipole magnet. Between the velo and the UT, there is a small magnetic field bending of those tracks, which are accounted for when looking for search windows. The upstream tracker is a 4-layer detector, and each layer has some sectors where you can identify the Y and X regions within the hits are falling. And given the projections of the input tracks, the algorithm is parallelized to look up to the sector ranges and then combine all the layers within the same sector ranges to build up the segments which will match the velo input track. Given that there is a small bending field, at this step, you also have an information with a resolution of around 20% of the momentum of the track that you have reconstructed. And you use this information to find the full track across the full spectrometer, which basically, after the upstream tracker, you integrate the whole magnetic field, and the track flies to the scintillating fiber tracker, which is composed by 12 layers. And given that you have information on the momentum, you can open a search window across all the layers and collect all the possible hits which could match the input track. You start combining the triplets from the 3 layers, having the bigger level arm between the 3 stations. And you select those triplets with some parameterization of the magnetic field within the psi-phi, and then those triplets are forwarded. All this happens in parallel. All triplets are constructed in parallels for each input track, and then you forward all triplet candidates to the other module. Now you have the full track passing the spectrometer, and you want to know if it's a muon, and this is what the muon AD does. You project the track that you have found in the psi-phi to the muon stations, and within a field of interest, you look for matching hits in the X and Y plane, and if all the stations are fired, you assign the muon tag to those tracks. Now you have all the tracks with the momentum and so on, and you need also the primary vertices in the events. Those are reconstructed starting with the velo tracks that I discussed a few slides back. And the algorithm has been developed for the CPU to get the maximum throughput, and has been ported to GPU. And it is based on an histogramming technique along the beam axis, where all velo tracks are projected to the point of closest approach. And then a peak finding algorithm finds the position of the vertices, and then the vertices are fitted, and here you can see the final resolution that we get on the primary vertex position in this real-time reconstruction using Allen as a function of the resolution in the X direction and the Z direction of the primary vertices. Now let me talk about the track reconstruction efficiency. This is a schema of the various sub-tracking algorithms that I've just described, Velo, Velo UT, and SciFi. And as you can see here, the performance in the Velo is excellent, almost 100%. So it's finding all the possible reconstructible tracks coming out from a BD case. Then in the Velo UT, you start doing some selections on the search windows and so on, which introduce this turn on, and then you do the SciFi track. Now for HLT1, what you care about is side transverse momentum tracks. So already here you can see that you are more above 90% efficient for the kind of tracks that you care about to take selections. But the tracking down to 0 PT is already implemented in Allen in the GPU, and this would cost only up to 20% extra on the GPU resources. And it will improve significantly the performance at low PT. Here it's the momentum resolution that you get out of this reconstruction sequence, which is below 1%, and it's pretty good as a function of momentum. And the neon AD efficiency, which is well above 90%, the primary vertex reconstruction efficiencies, which is as well pretty good, and the neon pion to neon misidentification efficiency as well. Now you have the tracks, you have the primary vertex, you have to take some selections for events to reduce the rate from 30 megahertz to 1 megahertz. And as you can see from this table, the pass-through is you let pass everything. So it's the input rate. It's a line, those blocks here is lines which are non-physics related in some extent, but are just operational ones. And the goal is to have all of those selections tunable such that you can ship out a 1 megahertz output rate. And as you can see from this table, this is achieved with this reconstruction and selection and so on. And several lines are already implemented for exclusive modes and calibration ones, as well the single track, track neon, and true tracks and so on. And then you can tune those lines to match the 1 megahertz output. And here you have a table with efficiencies that you get on several decay modes. And this already shows that this reconstruction sequence and selections is fulfilling a broad range of decays of interest for the LACD upgrade program. And ongoing, we are adding many more selections in this framework. Now let me talk about the performance, the computing performance of the HLT1 reconstruction. Here it's a throughput of the reconstruction sequence on various GPU cards, and
1 minute.
And the scale, yes, and the scaling of the throughut as a function of the theoretical 32-bit teraflops. And as you can see from the plot, the scaling is pretty good. So with new generation GPU cards, it's expected to further improve. And let me just highlight that this 30 megahertz reconstruction can be processed using 215 GPU cards, and the available slots are 500, meaning that there are large rooms still of improving this. And that's why I'm saying here that LACB is planning as well to expand the HLT1 reconstruction, adding as many more as possible algorithms like PID, long-lived track reconstruction, optimized track reconstruction for electrons. Now I land to the conclusion. I have not covered the full event reconstruction. I have some slides in the backup, but I hope I convinced that the LACB is almost ready to face the megahertz signal area, changing the trigger paradigm that goes from background rejection to signal selection and characterization. As Victor said, at the end of the chain, you do not anymore optimize for an event rate reduction, but a bandwidth reduction with the storage to this. And LACB has undergone a major detector and data acquisition system upgrade. The partial event reconstruction will be performed at 30 megahertz using GPUs, and the one performing the full event reconstruction with an input rate of 1 megahertz will be performed on CPU. And currently, the main topics LACB is covering is to improve the computing performance of the HLT2, add as many more selections as possible, and get ready for commissioning and possibly expand the GPU potentialities in HLT1 as much as possible. Thanks a lot for your attention.
Thank you very much. Questions? Please. Yeah, it's very interesting. Actually, Actually, why there is no more possible the hardware trigger? Like a very general question, or would it be possible to have a hardware trigger, and what hardware you would have to use for it?
So, I mean, the reason why we dropped the hardware trigger is because already in run 2, as you can see in this backup slide, on hadronic final states of the B hadron, in order to keep a readout limit of 1 megahertz, you had to start tightening up more and more the thresholds, limiting the capabilities of the detector itself at increasing luminosity. So the point is that the signal rate is so high that a single subdetector will not be possible in principle to select efficient events. So you want to have the flexibility to switch between one decay mode and another and optimize based on the physics case that probably during the run period will become more and more important for the LACD physics program. I think this is one of the key aspects of having at the
So I would expect that before you start to
Yes, I cannot hear anymore.
Yes, I lost you too.
Can you still hear me?
I can hear you, but I cannot hear Yeji.
I'm sorry, can you hear me now?
Yes.
Oh, thanks. Sorry, my Zoom is slightly bad. So my question was, if you actually before you start the upgrade of your hardware, if it was already optimized for this plan with for the triggering.
Yeah, so let's say that the hardware update were necessary because of the higher occupants in the various subdetectors, and also to be able to get the readout at 40 megahertz. So the whole upgrade consisted in upgrading the tracking subdetectors. So for example, in the Velo using pixel sensors instead of RFI sensors, improve the momentum resolution in the Velo UT stage such that you can take some selections and optimize the search windows for the full tracking. So some studies were done on the way to structure your subdetectors to get a reconstruction sequence which was hopefully fast enough and you can decode the detector fastly enough. But then the reconstruction sequence is very similar to what you do in run 1, run 2, but with different detectors. So many developments and improvements on them has been put in place, taking advantage of the, for example, that in the Velo you get directly XYZ, while before you had to combine more information to get a position. And yeah, I mean, the detector upgrade that has been done was necessary to cope for the higher multiplicity and higher occupancy in the various subdetectors and sustain the radiation environment and so on. Then algorithms have been written for the upgrade, were working quite well, but they were super slow. And then we have spent a lot of time and energies on developing the multi-threaded framework for CPUs, parallelizing algorithms with CMD instruction and so on. And then 2 years ago, the GPU project appeared and all the reconstruction sequence has been re-implemented with some more freedom with respect to the framework that was shared between HLT1 and HLT2, which allows to shuffle around the data structures you were dealing with to optimally parallelize the algorithms. So in some extent, the only interplay between detector and software is the way in which you ship your subdetector readout and the links. So you get, for example, in some subdetectors, hits which are already sorted by construction. So you don't need to resort things at software. So those are the kind of tweaks that has been done in a later stage with respect to the detector themselves.
Okay, thank you very much. Thanks. Thank you. And so we have a time to move to other presentation. So we will move from LHCb now to Bell. So Bell 2, and it should be Petar.
Yes, just to confirm, are you able to hear me and see my slides?
Perfectly.
Okay, very nice. Okay, let me begin. So good morning or good evening to you all, depending on your time zone. And in this talk, I will be presenting the measurement of the Bell 2 trigger efficiency, more specifically the level 1 efficiency for tau pair events. Okay, let's begin with a brief overview of SuperCAC-B. So SuperCAC-B is an energy asymmetric electron-positron accelerator located at KEK in Tsukuba, Japan. And the facility will enable searches for new physics by studying B, D, and tau lepton decays. And it represents a major upgrade of the prior CAC-B accelerator. For example, it has higher beam currents, and it utilizes the so-called nanobeam scheme. So the capacity to reach a 50 nanometer vertical beam spot size during the collisions. And this will allow it to reach an unprecedented luminosity of around 6 by 10 to the 35, which is roughly 30 times higher than at CAC-B. In fact, if you're not aware, just last month, SuperCAC-B broke the peak luminosity world record. And in 2016, the accelerator had its first beams in commissioning. In 2017, the Bell 2 detector was rolled into the collision point, and it recorded its first collisions in April of 2018. Okay, on the right here, you can see a diagram of the Bell 2 detector. So it keeps the general design of the previous Bell detector, but with some major upgrades to its subsystems. So the vertex detector is located closest to the collision point, and it currently consists of effectively 1 pixel layer and 4 layers of silicon strips that together provide improved tracking and vertex resolution. Then going further out comes the central drift chamber, so CDC, which has a larger volume with smaller drift cells compared to Bell. And then further out, there are the new A-Rich and top systems that provide improved particle ID in the forward and barrel regions. And then surrounding this is the electromagnetic calorimeter. And then finally, furthest away from the collision point is the K-long and muon detector. Okay, so Bell 2 began its so-called phase 3 of data taking in March of last year. And this figure here summarizes the weekly recorded and total integrated luminosity during this period. So as you can see, we've recorded around 74 inverse femtobarns so far. And the results I will show today are only for the 2019 data sets, so around 9 inverse femtobarns. So we are still in the very early stages of the Bell 2 program, and over the next 10 or so years, we aim to collect 50 inverse attobahns of data, which is a factor of 50 more than at Bell. Okay, so SuperCAC-B delivers events at a rate that goes beyond the capacities of the data collection network and the data storage systems of Bell 2. And at the design luminosity, the physics rate is around 20 kilohertz. So the table on the right shows the breakdown of this rate amongst different physics processes. And as you can see, tau pair production makes up around 3% of this rate, sorry. There is also the machine background to contend with, so which are much larger than at Bell, and they come mainly from Touchek and beam gas scattering. And together, they increase the trigger rate significantly. And the hardware level 1 performs the critical task of reducing the average physics plus background rate to a maximum of 30 kilohertz. And the requirements of this system are high efficiency, not only for high, but also for low multiplicity physics, a fixed latency of about 5 microseconds, a timing precision of 10 nanoseconds, of less than 10 nanoseconds, and a minimum 2-event separation of 200 nanoseconds. Okay, and on the right here, you can see a schematic overview of the level 1 trigger. Roughly speaking, there are 4 sub-triggers that send their outputs to the global decision logic, where the final online trigger decision is made. And the 2 main sub-triggers which are studied here in this, what's shown in this presentation are the CDC and ECL triggers, which are highlighted here in blue. And the main function of the CDC trigger is 2D track finding, while for the ECL trigger, it computes the total energy sum finds isolated clusters and identifies bar-like events, for example. I'll give some more details in the coming slides. Okay, so tau pair events provide a nice test bed of the L1 performance in the early data for low multiplicity physics. So first of all, tau pair production has a relatively large cross-section. And also with tau decays, you get a wide variety of low multiplicity signatures with tracks, so electrons, muons, and pions, and the clusters, so also including the pi zeros. And here I summarize how we reconstruct the tau pair events for this trigger study. First, we require the tracks to be either 1/3 or 1/1 with respect to the thrust axis, as shown in this diagram on the left. Then we reconstruct 6 decay channels depending on whether the tracks originate from electrons, muons, or pions. So we use light blue ID. For 1/3 prong decays, so 4 track events, we consider the E3 pi, mu3 pi, and pi3 pi channels. Whereas for the 2 track events, so 1/1 prong, we consider the E mu, mu pi, and mu channels. We then apply some additional selections to suppress the non-tau backgrounds. So for example, for 1/3 prong events, we require the thrust value to be above some value, to help suppress the QQ bar, as you can see here. And also we apply some upper threshold on the total visible energy to suppress mainly radiative bar events. Several other selections are applied, which I list here, including cuts on the number of reconstructed pi zeros and additional high energy photons in each hemisphere. Okay, now let's go into some results. So here I show the overall level 1 efficiency for 1/3 prong events for several combinations of unprescaled CDC and ECL triggers. So keep in mind that the trigger decision is made independently using only the CDC information or ECL information. And this allows us to perform a data-based measurement of the per event trigger efficiency. So the strategy as shown in this equation is to measure a particular trigger's efficiency with respect to a set of orthogonal reference triggers. So for CDC triggers, we use the ECL triggers as a reference and vice versa. The trigger combinations that are shown in this plot are those that we found to have the highest efficiency for the tau events. So going from left to right, they include the CDC triggers that require at least 2 or at least 3 full tracks. The short track triggers, so I'll explain full and short tracks a bit later. The ECL energy threshold, cluster counting, cluster topology, cluster energy, and finally ECL dimuon trigger. And as you can see, the CDC triggers perform rather well in all 3 channels. And as you would expect, the ECL energy threshold trigger has highest efficiency where there is an electron on the 1 prong side, shown here in blue. And the cluster counting triggers perform well, especially in the pi3 pi channels, where you have more clusters from the pi zeros, so shown here in green. On the next slide, I show the same thing, but for the 1/1 prong decays. Here again, as you would expect, the CDC trigger, which requires at least 2 full tracks, has high efficiency. And the trends for the ECL triggers are sort of similar to before. So where we have an electron, the energy sum trigger has highest efficiency. And where we have more pi zeros, the cluster counting triggers perform better, generally speaking. Okay, the main CDC triggers target what I called before full tracks. So these tracks pass through all the axial CDC superlayers and reach the barrel, as shown in this bottom left figure. As a result, the full track triggers will have a drop in efficiency in the end cap. So this can be seen by looking at the blue points in these 2 plots, which show the per event efficiency as a function of the theta of the track with minimum PT. And to compensate for this drop in efficiency, we have so-called short track triggers, which have been operational since October last year. And here, short tracks are those that pass through the innermost 5 axial plus stereo superlayers, reaching the end caps or curling back inside the barrel. And as you can see, by comparing the blue and orange, the short tracks provide a significant boost in the efficiency, ranging from 5 to 40%, depending on the track theta. Here I show the same thing, but as a function of track PT. And as you can see, by comparing again blue and orange, the short tracks provide a substantial gain in efficiency, especially for low PT. And of course, this will have a positive impact on tau and other low multiplicity physics. Another important class of triggers for tau physics are the ECL energy threshold triggers. So here a sum is performed over what we call trigger cells. So these are trigger towers of 4x4 crystal granularity. And the current lowest energy unprescaled trigger has a 1 GeV energy threshold. And this performs well for tau pair events that deposit the most energy in the ECL. So as we saw earlier, I think on slides 5 and 6 or so, this includes the tau to E nu leptonic modes and the hadronic modes, including the pi zeros. On the right here, you can see the overall efficiency for this trigger as a function of the total cluster energy. And as we expect, we see quite a sharp turn on at around 1 GeV. We do observe some drop in efficiency at high energy, especially for 1x3 prong events. We suspect this is coming from the bar veto requirement, which is constantly in a state of development. So this will improve in the future. So far we have seen the trigger performance for standard model tau decays, but now let's look at a particular example of a new physics search. So first, some motivation. So due to neutrino oscillation, we know that lepton flavor violation occurs in the neutrino sector, but so far we have no experimental evidence for LFV with the charged leptons. If we minimally extend the standard model to include neutrino masses, then charged LFV can occur through loops, as shown here, but this is suppressed to the 4th power of the neutrino masses. So its branching ratios are too small to ever be observed. However, if we did observe some signature of charged LFV, then this would definitely be some indication of new physics. So as you can see here on the right, the mu to E transitions have already been heavily constrained. On the other hand, the tau transitions, shown in blue, have weaker bounds coming mainly from Bell and Barber. And new physics can typically enter at the 10 to the -10 or -7 level, where Bell and Barber were already entering the interesting regime. So sensitivity studies for Bell 2 indicate that it will push the current tau LFV bounds forward by at least 1 order of magnitude. And one of the golden channels for tau LFV discovery is tau to 3 muons. You can find more details on this search in the talk by Inami-san on Friday. Now, tau to 3 mu is one of the more challenging signatures to trigger on at level 1. And to study the L1 efficiency for this signature in real data, our strategy was to use the standard model 1x3 prong tau decays, so 3 pions instead of 3 muons. And the events were then required to pass the similar signal selections to the LFV search, which are listed here. So in this way, the standard model process is made to have LFV-like kinematics. So in Bell 2, we have several new, what we call low multiplicity ECL triggers that have requirements on, for example, the number of clusters, the cluster theta region, energy, and topology. And amongst these triggers, we have found that the at least 3 cluster trigger performs best. On the right here, you can see the measured efficiency for this particular trigger as a function of the delta E on the signal side tau. And
1 minute.
Yeah, almost finished. And where we expect the signal, so around delta E equals 0 in this orange region, we reach an efficiency of around 95%, which outperforms quite a bit the CDC triggers, which are typically used in these kinds of analyses. On this slide, I show the same thing, but split according to whether the 1 prong track is identified as a muon, electron, or pion. And here, as you would expect, the plateau efficiency is higher, where we have the more highly energetic electron cluster, or where we have more clusters coming from additional pi zeros. Okay, this brings me to my final slide. So yeah, the level 1 trigger system plays a very important role in enabling tau and other low multiplicity physics at Bell 2. We have studied the L1 efficiency in tau pair events, so 1x3 and 1x1 prong decays. And we observe overall good performance in the early data. You can find the recent public plots here. We observe some drop in the CDC full track triggers, when we have at least one of the tracks in the end caps. This is also the case in Bell 1, and it impacts most the 1x1 prong events. And we have some new short track triggers which show great promise. And we have some new ECL low multiplicity triggers, which, as we have seen, will play an important role in upcoming tau LFV results from Bell 2. Just very briefly, the topic of this talk is mainly performance, but there are some level 1 developments in the pipeline coming mainly relating to the CDC trigger. So generally speaking, we now try to reduce the background rates by utilizing 3D tracking at level 1. In particular, there is this Neuro Z trigger, which is trained on data to compute the Z0 within the level 1 latency and with a good resolution with respect to offline. And with this, it should be able to keep the level 1 rates significantly lower, which is, of course, very important once the luminosity really starts ramping up. And this will keep the, hopefully keep the triggers unprescaled and the thresholds as low as possible, which is important for tau and low multiplicity physics. Okay, that's all for me. Thanks a lot for listening.
Thank you very much. Very nice presentation. Quick question. Okay, I would have maybe the quick question. So why actually the silicon tracker is not included in this hardware trigger or level 1 trigger?
I think it's, I mean, I'm not necessarily an expert on this, but I suspect it's an issue with readout limitations. So lots of the, let's say the main components of the level 1 Bell 2 trigger was inherited from Bell 1. And it was decided that it wouldn't be feasible to have the readout be high enough to facilitate using, definitely not the PXD or even the SVD. I'm not sure if there, I think it's a really hard limitation, but perhaps people are thinking maybe in the longer future to perhaps include this, but for now it's not feasible. Yeah.
Okay, thanks. Thank you very much again. So we'll move to other talk, which will be Mario from Atlas.
Yes, hi, can you hear me?
Yes, you can try to share.
Yeah. Okay, can you see that?
Yes.
Okay, perfect. So as I said, my name is Mario Grandi. I will be presenting the Atlas inner detector trigger performance in proton-proton collisions at 13 TeV during the LHC Run 2 on behalf of the Atlas collaboration. So let me begin by highlighting the importance of triggers in Atlas. So here I have the invariant mass distribution for leptons from the decay process of Higgs to 4 leptons using the full Run 2 dataset. The level of precision shown here is only possible because of the high performance of the leptonic triggers. And it's important to stress that every event was selected because of the successful operation of the tracking in the leptonic triggers. So the track and vertex reconstruction within the Atlas detector is done by the inner detector, which is a dedicated Atlas subdetector. And it consists of 3 subsystems. The pixel detector, which is the closest to the beamline and the interaction point, and is shown in the diagram by the dark green and lighter green bands, which consists of 3 layers of barrel and end cap silicon pixel modules and an insertable B layer, which was added in Run 2. Then in the blue band, we have the semiconductor tracker, which consists of 4 barrel and 9 end cap layers of silicon microstrip modules. And finally, in the orange band, we have the transition radiation tracker, which consists of a barrel and end cap modules of straw drift tubes. So the Atlas trigger system is separated into a hardware stage called level 1, which identifies region of interest, and a software stage called high level trigger, which processes these ROIs identified by the level 1. So the ID trigger is part of the HLT system and performs the online track and vertex finding. And it's important to highlight that these tracks are essential in triggers for nearly all physics signatures, and that as pileup increases, tracking becomes even more important, and that is the most complex aspect of the trigger and very computationally intensive. So one of the main tasks for the HLT is that it needs to reduce the peak data rates from approximately 100 kilohertz down to approximately 1.5 kilohertz. And that the pixel and SCT cannot be read out in L1, and the earliest is in the HLT. So to ensure the speed while maintaining high performance, two main strategies are used. There's a baseline single stage strategy, which consists of a data preparation stage, where the detector elements are reconstructed for a given spatial ROI. Then it's then followed by a fast tracking stage, where the fast track finder algorithm is run, which is optimized for track finding efficiency and providing initial track fit and track parameters. And finally, it's followed by a precision tracking algorithm, which applies the offline track fit using tracks from the fast track finder and extends them to the TRT and runs ambiguity solver algorithms to remove duplicate tracks. The other strategy is the multi-stage strategy, which is used for more complex objects such as tau or BJets, and consists of two stages. So the first stage, in the first stage, it performs an initial fast track finder tracking algorithm in a narrow width ROI, but extended along the entire beamline, as shown in the diagram on the left by the dark purple area. And there it determines tracks or vertex of interest. It then is followed by the second stage, where the tracks identified in the first region of interest are used as seed for the second ROI, which is in a narrow range along the beamline, but wider in E10.5, as shown in the diagram on the left now with the blue area. In this new ROI, it then performs the second stage FTF, and then which is then followed by the precision tracking again. So what we find is for when tracking muons with PILAP with mean PILAP of 52, is that the fast track finder runs on average in around 40 milliseconds per ROI. On the other hand, the precision tracking only runs on average in approximately 7 milliseconds per ROI, as it uses the tracks seeded from the FTF. In this diagram, I'm also showing the isolation tracking, which is run in a wider ROI after selection of full muon candidates to establish muon isolation. And so this runs on average in approximately 116 milliseconds per ROI due to this. On the other hand, the multi-stage tracking for a tau trigger reduces the fast track finder computation time from approximately 66 milliseconds when run as a single stage down to, on average, to approximately 46 milliseconds if we combine the first and second stage. This is because although part of the detector about the tau track is processed twice, the overall volume is lower than if done by a single stage. So the tracking efficiency and resolutions are measured by comparing the tracks found by the online trigger algorithms to the tracks found by the full offline track reconstruction. A tag and probe analysis is used to select muons candidates coming from the decay of the Z boson, where the tag muon is fully selected in a muon spectrometer and inner detector, whereas the probe muon is selected based on the muon spectrometer reconstruction alone, without the use of the inner detector trigger tracks, and therefore is completely unbiased by the inner detector reconstruction. So what we find is that we have very high efficiencies, even up to 1 TeV in track momentum, and above 99% efficiencies, even at large transverse impact parameter values. As well, we have very good resolutions that are better than 20 micrometers for full range observability values for the muons. Similarly to the muons, for the electrons, we use an electron tag and probe consistent with the Z mass, and this greatly reduces the background for fake electron candidates. And so we have very high efficiencies for the full PT spectrums. In fact, for electrons with transverse energy above 15 GeV that have radiated up to 80% of their energy as photons, we still have efficiencies above 98%. So something to note is that the transverse electrons with transverse energy over transverse momentum, which from now on I will just refer to as ET over PT for simplicity. So electrons with ET over PT above 1 show Bremsstrahlung electrons. So these are electrons that have radiated away some of their energy via photons. And so they have a PT value below the deposited ET. On the other hand, electrons that have ET over PT below 1 indicate electrons with less well-reconstructed trap PT. This is electrons that have a PT that is actually greater than their deposited energy. And so in our analysis, we were able to remove these electrons. Yes, for the one-prong tau 25 GeV trigger, we have efficiency is better than 99% across all pseudo-resistivity values and in the full range of PT. It is important to note, I should mention, for both the first stage and second stage of the multi-stage strategy. It is important to note, however, that the second stage fast tracking resolution is actually better than the first stage at lower PT. This is due to the fact that low momentum tracks bend out of the narrower first stage ROI in the magnetic field, and so they're not fully reconstructed, but they are then picked up by the second stage, which is why there's it has a better resolution. It is also important, very important to note that we observe very high efficiencies, which are approximately constant for the full range of pileup interaction multiplicities, even at very high pileup interactions, multiplicities. For the B-jets, the vertex reconstruction runs two algorithms, a simple histogramming algorithm and an offline-based vertex algorithm. The histogramming algorithm has a higher efficiency for low track multiplicities, and this is due to a softer requirement of track qualities, which allow for reconstruction of vertices with lower track multiplicity. On the other hand, the offline-based algorithm has a better resolution, which is as good as 20 micrometers for longitudinal impact parameter, with increasing vertex track multiplicities. We also find very good resolutions for B-jet tracking for longitudinal in-track parameters. So we see that it's actually better than 12 micrometers for the full range, full PT spectrum for the precision tracking, although we find that it's slightly lower for the fast tracking, but that's expected. So to recap, the ID trigger is fundamental to achieving the required performance of the Atlas trigger system. I've shown the performance in terms of efficiency, resolution, and processing time for the most important tracking related signatures for the high luminosity run 2, and shown the excellent tracking performance that has been observed in high pileup multiplicities. In fact, I've shown that the tracking efficiency seems largely independent of pileup interaction multiplicity. Therefore, the ID trigger continues to provide excellent performance in run 2, outperforming the already excellent performance in run 1, and thus allowing the continuation of the Atlas physics program. I would like to also highlight that to handle the expected conditions of LHC Run 3, there are ongoing changes to the Atlas software infrastructures to make use of the new developments and allow increased use of multi-threadings. And so the ID triggers are undergoing an extensive re-implementation of many aspects of the processing. So this concludes my presentation. Thank you very much for listening.
Thank you very much. Very nice presentation. Questions? Actually, I would have a question. So, very general question. Why at the moment or currently for Atlas, the inner detector is not the part of the level 1 trigger? Why it is used only for this high level trigger? It is because of the bandwidth or the speed?
Yeah, I believe that's the case. It's due to the processing time that's required to access the different parts of the inner detector and reconstruct the objects. Okay.
However, for the high luminosity LAT and with the inner tracker that is planned, I think that the inner tracker should be the part of the level 0, the new level 0 trigger. So you know why it will be possible?
Well, I'm afraid I'm not an expert on this, so I'm
okay.
I do not want to comment on something that.
But you mentioned that already for run 3, there are
yeah.
significant changes planned. So
yes.
what is the main thing?
So the main thing is that we're implementing the multi-threading into the whole Atlas software infrastructure.
Okay, we will probably hear about
Yes, I believe so.
Okay. Thanks a lot. Thank you again.
No problem. Thank you.
And we will move to other Atlas presentation will be given by Kate.
Hello, can you hear me?
Yes, you can try to share.
Sure, just 1 second. Okay, can you see the slides now?
Yes.
Okay, so I'll be discussing the phase 1 upgrade of the level 1 calorimeter trigger. So I move to slide 2. The Atlas trigger system is a 2-level trigger system which selects interesting events for offline analysis. So the first level is a hardware-based level 1 trigger, which has a very low latency and performs a course selection using a limited amount of information from the detector, so only from the calorimeters and the muon detectors. The second level, the high-level trigger, or HLT, is a commercial CPU farm, which performs a more refined selection using the full detector information. So the combination of these two systems reduces the event rate from 40 megahertz, the collision rate, down to 100 kilohertz at level 1, and finally to 1.5 kilohertz after the HLT selection. And this is what is actually written out to storage. So on slide 3, I'll give a little bit of motivation for why we're upgrading our system. Triggering in high pileup environments is very challenging. You can see from the pileup plot here in the bottom right-hand corner, the pileup is increasing year by year, and the luminosity of the LHC is already exceeding its design value, so we need to keep up with this. The physics motivation for the phase 1 upgrade, which Atlas is currently undergoing, is based on numerous different physics analyses and searches. So for example, missing ET and multi-jet trigger rates are very vulnerable to pileup, and these are important for SUSY beyond the standard model and invisible searches. Identification of isolated objects is also very important for electroweak measurements, and this is challenging in high pileup environments. And finally, there are a lot of studies of unique signatures for things like vector boson fusion or long-lived particles, which are becoming very popular right now, and these really benefit from specialized triggers as well. So one issue for run 3 is that because of detector readout limitations, our level 1 trigger rate is fixed at a maximum of 100 kilohertz. So it's really important for us to be able to reject pileup while still maintaining low trigger thresholds in order to avoid losing any of this interesting physics. On slide 4, I'll introduce the level 1 calorimeter trigger. So this identifies calorimeter-based physics objects like electrons and photons, taus, jets, missing ET, and ET sums. The trigger objects, which are identified by this system, are then sent to the level 1 topological trigger, or L1 topo, which performs some additional selections, which I'll discuss a little bit later. And the object multiplicities are sent to the level 1 central trigger for the final one, level 1 accept decision. On slide 5, I'll explain the motivation for why we're upgrading this system. So as I said before, the level 1 trigger rates are very vulnerable to pileup. And as Pavel showed earlier in this session, the liquid argon calorimeter is also being upgraded to provide higher granularity inputs to our trigger system. So if you look at this diagram here on the left, in run 1 and run 2, the inputs to the level 1 calo trigger were trigger towers, which measured 0.1 by 0.1 in eta and phi. And then if you zoom in on a single trigger tower here, in run 3, this is split into 10 supercells. So you have subdivision into calorimeter layers, and also in the first and second layers of the calorimeter where the bulk of the shower energy is deposited, it's more finely segmented in eta. So this gives us a good handle on identifying isolated objects. So to exploit all of this new higher granularity in the calorimeter, In level 1 Calo, we've introduced new ATCA-based feature extractors or FEXs, which are able to run more sophisticated algorithms. They have a much larger optical input bandwidth than the previous system. They have improved isolation performance and pilot robustness, and this will allow us to reduce our rates while still keeping our trigger thresholds low. So you might have noticed in this sketch of the system here, you can see in yellow highlighting the parts of the system which are running in run 3. And then I also show in this green and blue at the bottom of the diagram, the legacy systems from run 1 and run 2. And the two systems will actually run in parallel during the commissioning phase. And once the new run 3 system has been fully commissioned and is ready to provide triggers for physics, then the legacy system will be removed. So on the next couple of slides, I will introduce the feature extractors a little bit, starting with the EFEX, the electron feature extractor. So this identifies isolated E gamma and tau objects and consists of 24 ATCA modules, and you can see an example of one on the right. So this system exploits the full calorimeter granularity in each layer and allows us to perform more sophisticated clustering algorithms, and we can compute the isolation of objects using shower shape observables. And this gives us a significant rate saving at level 1. So this plot here on the bottom left, the points in black show a turn-on curve for the EM trigger that was used at level 1 in run 2. And then the blue and the red show a couple of different examples of thresholds. So for example, the blue gives us the same rate as run 2, but with a much lower threshold. And the red curve gives us a reduced rate with respect to run 2, but the turn-on threshold is at the same point. So this will be really beneficial for physics with EM objects. On slide 7, the next FEX is the JFEX, or jet feature extractor. So this identifies jets, but also missing ET sums, and hadronically decaying taus. And this consists of 6 modules with a full eta phi coverage. The calorimeter inputs to this trigger are 0.1 by 0.1 trigger towers. So if you look at the cartoon on the top here, the run 2 system had 0.2 by 0.2 inputs, whereas the run 3 system has more finely granular inputs. And also you'll notice that it is able to run more sophisticated round jet algorithms as opposed to this basic square shape, which we had in run 2. And this can look at either small radius jets or large radius jets. In addition, the JFEX can perform noise suppression and pileup subtraction, and this will mitigate the impact of pileup on missing ET and multi-jet triggers. I show a performance plot here at the bottom right. This is with a di-Higgs to 4B sample simulation, and you can see the level 1 trigger that was used in run 2 is given by the black points, and the run 3 JFEX curve is shown in blue here, and you can see that for close by jets, so you have an offline selection of PT greater than 30 GeV and at least one jet within delta R of 0.6, and online requiring 3 jets, you can see you have better performance for close by jets. So this will be very useful for this type of search. Finally, on slide 8, the GFEX, or global feature extractor. And this is a bit different in that it's a single ATCA board, which is processing the full calorimeter coverage. And because it's only a single board, you can exploit full scan algorithms to compute global event quantities. So we can use more sophisticated algorithms for missing ET. We will use one which is based on the jets without jets. I give a link to the paper describing this here. You can also compute things like the pileup density rho, for example. And this is particularly useful for physics with boosted objects. So it can compute jet substructure quantities. If you look at the plot in the bottom left, I show in this blue square here, we have a Z prime to TT bar event, and the run 2 level 1 jet trigger would only be able to capture the information which is in this blue square, whereas with a large R jet trigger from the GFEX in run 3, you would have access to everything in this black circle, so you would have much more substructure information about this event. On slide 9, the level 1 topological trigger was introduced in run 2 and commissioned and provided triggers for physics. The boards have been redesigned for run 3 using a design based on the JFEX modules, and these will provide more processing power and additional functionality with respect to the legacy version. So this is a really useful trigger because it provides additional background rejection and high signal efficiency without raising thresholds. And it does this using topological cuts. So the inputs are objects not only from the level 1 Calo system, but also from the level 1 muon trigger system. And it can apply selections on things like invariant mass, angular cuts, and it can also look at late objects from other bunch crossings. So in these plots on the bottom, I show a few examples of things that L1 topo can do. The first plot on the left is a B physics trigger, which applies dimuon selection. And you can see if you compare the blue and the red curves, by adding an angular cut and an invariant mass selection, you can reduce the rate without actually raising the PT threshold. In the middle, I have a plot of a large R jet trigger efficiency. So if you compare the solid points, which show a selection on some ET in a cone of delta R of 1 versus the open points here, which just have an ET selection, you can see that the trigger efficiency is actually recovered for events with at least 2 subjets. And then finally on the right, I have an example of a turn-on curve for a trigger for a unique signature. This is a VBF Higgs trigger, which combines angular and invariant mass selections. And this is an example of how this kind of selection can be used for physics analyses involving challenging signatures. On slide 10, in addition to the new feature extractor modules, we're also adding some new infrastructure. So in order to cope with the vast number of optical fibers that are coming from the calorimeters to the FEXs, we have the FOX fiber optic exchange, and then a similar topo FOX, which maps the fibers from the level 1 Calo and muon systems to L1 topo. We also have the T-Rex system, which will transmit digitized information from the tile calorimeter to the level 1 Calo system. And then we also have some new control and clock hub and readout systems. And the readout will be done via the new Felix system, which is being used in several experiments. On slide 11, I'll say a few words about commissioning and installation. So commissioning has been taking place at CERN in our surface test facility. Unfortunately, due to the COVID shutdown, we had to leave the facility for several months, but progress is picking up once again. We are back in the lab, and our goal is to achieve a fully integrated vertical slice with synchronized data transmission on the real-time and readout paths. So we're performing a number of different tests in this facility. We take digital inputs from the LAR calorimeters. And we also have FEX test modules, which provide test patterns. And then we send these to the eFEX, JFEX, and GFEX, to L1 topo, and then to the readout. And we perform hardware, firmware, online software tests, fiber mapping tests, and all of these are underway at the moment in our lab. On slide 12, just a few words about what comes next. So as we're moving from the Run 2 system to the Run 3 system, I mentioned before that these two systems will actually run in parallel during commissioning with beams in the startup of Run 3, and the legacy system will be removed once the phase 1 system is fully commissioned and providing physics triggers. So this will be a very lengthy process. So currently we are recommissioning our legacy system and of course also commissioning the Run 3 system in the lab. In the second half of this year, we will be installing the system underground in the Atlas cavern. And this will of course require well-tested hardware. Then the next step in the commissioning phase will be internal testing. So testing the connectivity and configuration and mapping of the fibers in the individual modules. Then from there, we move to integration with the calorimeters, which of course requires functioning readout and TDAC control. Then we move to integrating with the full Atlas system, which will be, of course, a very gradual iterative process. We will do beamless commissioning with cosmic data. And then once the LHC starts up, we will do commissioning with beams, which of course is a very careful process. This requires good monitoring to catch all of these rare bugs, and timing calibration, of course, will also be critical. And then the end goal will be to provide robust and efficient triggers for physics in run 3. So that's it for me. Thanks very much for listening.
Thank you very much. Very nice presentation. Questions? Okay, so I would have a question. So you mentioned that, of course, the calorimeter and muon chambers are the part of the level 1 trigger at the moment for the current Atlas detector. The tile color is not?
Yes, the tile calorimeter is also part of the level 1 trigger.
Okay, then I would like to ask, what is the increase of the granularity of eCal, the plan for run 3?
For the EM calorimeter?
Yeah, it's like 10 times or?
Yeah, let me go back on slide 5. So you can see this cartoon in the bottom left. The run 1 and run 2 is shown on the left, and then on the right you have the run 3 system. So you go from a single trigger tower input, which is subdivided into 10 supercells, and it's more finely granular in the region which receives the most of the energy deposit.
Is this done by like really physically changing these active volumes, or it is like only by the readout channels or the change of the readout electronics?
Yeah, this is a change in the liquid argon electronics.
Okay, okay. And last question, what is the expectation for the high luminosity, or what is the plan? Because you mentioned also the Felix readout, which I know will be also the solution for in a tracker.
Yeah, so the run 3 level 1 calorimeter system that we will use in run 3 will also be used in run 4 for the HLLHC. So the design has
upgrade planned?
Well, the design has been made with run 4 in mind. There will be an additional feature extractor which will be added for forward electrons, the FX, which I didn't touch on here.
Okay, thank you very much. Yeah, very nice. Thanks.
Thank you.
Okay, so we will continue with Atlas, and we have triggering on hadronic signatures with the Atlas detector. Benjamin. Oh.
Hi, can you hear me?
Yes, perfect.
Okay.
Yeah, we can see you. If you can try to share.
Yeah, I'll share.
Perfect.
You can see the slides, okay?
Yes.
Okay. So I'm Ben Carlson. I'll talk about triggering on hadronic signatures with Atlas. So the basic theme of this talk in terms of physics motivation is things like dark matter. For example, we know from astrophysics that there's additional matter that can be explained by standard model. We have models like supersymmetry. And of course, because this is a trigger talk, we also want to trigger on the standard model. And so all of these are important physics motivations. What I'll do is I'll talk about the Atlas trigger, which you've seen a number of times already. I'll emphasize a few different details about level 1, as those will impact some of the features I'll talk about for jets and missing ET. So you've seen this before, but the basic argument for the Atlas trigger is that we have a large data rate coming in because we have relatively large events. And in principle, we can have an event rate of up to 40 megahertz if every bunch crossing was filled. So then what we do is we have a two-tier trigger or a two-level trigger where we have events in a on-detector buffer, which then some information is sent to the level 1 trigger where we use FPGAs to do very fast calculations with just the calorimeter and muon system to reduce the rate to 100 kilohertz. And we can read out 100 kilohertz of these event buffers. Any more than that, then it introduces dead time, which comes back to an earlier question about why we can't utilize tracking information in our detector because we can't actually retrieve the information. So then once the information is saved, it goes into permanent or temporary storage in disks, and we access that information using software. So to give a little more information about level 1, which I'll need to explain some of the improvements that we did in run 2, the input to the trigger system is roughly 0.1 by 0.1 granularity for most of the detector. And this is done by taking the liquid argon and tile subdetectors, which are much more granular, and having analog sums done to get to the higher granularity. So the input to the level 1 system is actually digital or analog information as well. And then the first thing we do is actually digitize it. So we have sampling in 25 nanoseconds or 80 or 12.5 nanosecond sampling, digitize it, and then run some filters to reduce the impact of out-of-time pileup, apply a correction to shape the bunch crossing dependence, and then apply some threshold to remove pileup just using ET. Then we do things like identify jets and missing ET and electrons and show jets. We also have the ability to combine information from the level 1 system in the level 1 topological processor, where we can calculate mass and do other calculations, which I'll mention. So we'll talk about jets next. I'll mention the motivation. I'll talk about single jet triggers, large radius jet triggers, and vector boson fusion. So this is a very extreme event. This is a dijet event that has a mass of 8 TeV. And this might come from dark matter. For example, you have a mediator that's a Z prime that couples only to quarks, and then you get dijet events that look like this. Now, one way to think about jet triggers, it's not the only use, but one way to think about them is in terms of searching for dark matter. The event display on the previous slide came from very high mass, but in principle, we want to probe the whole range of mass. And so the way to do that is to split this up into different triggers. So for example, if you have a single jet, you can trigger on the high mass part. The other parts of this require different triggers. And so I'll also mention the very low mass part, which uses a large radius jet. And so we have improvements on that, and so I'll mention that as well. So for single jets, at level 1, we have an unfree-scale trigger that's fully efficient by around 200 GeV offline. And then for the high-level trigger, it's after taking into account improvements in calibration, which utilize things like detector response across pseudo rapidity. And then once we calibrate those differences away, we end up with the red line. Now in the HLT, we do have some tracking information, so we can utilize those tracks to get a slightly better calibration, which is shown in blue. And you can also see that there's a really big gap between these two, which is an important feature for some analyses. For large radius jets, we also have triggers both at level 1 and the high level trigger for this. The physics case is similar. Again, you have the same kind of Z prime model decaying to quarks, which are jets, but if you boost the system with an ISR jet, then they can be collimated into a single roughly radius 1 cone. And so at level 1, to get around the issue of the fact that our jets are a little bit too small to capture this, what we do is take all of those jets in the topological trigger, or L1 topo, sum their ETs together if they're within a cone of radius 1. And then that allows us to improve the efficiency of the large radius jet triggers. And you can see that on the left-hand part of the plot. And it improves the efficiency by about 20 to 30 GeV for the same rate compared to level 1 just by itself. And that's shown in the back of the if you're interested. Another feature of this plot is that you see the biggest improvement when there are multiple subjets, like for example, a TT bar decay. The right-hand side shows the HLT efficiency. We also have large radius jet triggers here. Of course, much higher threshold. We can get around that a little bit by requiring 2 jets, where there's a mass requirement on both jets. That removes a lot of the QCD background. So we've improved a lot, but of course, you can also just look at these two plots and see that HLT is not on top of level 1. So we can, in principle, get more clever and attack these cases depending on the physics case. The last one is vector boson fusion. So this is also a jet trigger. The physics motivation here is that we have vector boson fusion Higgs events, but the Higgs decays are too soft. So this might decay to 4p jets. It might be something long-lived that you can't trigger on otherwise. And we utilize these 2 jets and evaluate the dijet mass in the L1 topo trigger. And you can do it using this simplified expression. There's also a delta phi term. And calculate approximate mass. So we did that. And this is the efficiency curve for that trigger, but also after the HLT. So the HLT has the same basic selections and a delta phi cut to reduce the QCD rate because we don't have any other requirements in this trigger. And after all of the selections, it's fully efficient by about 1.3 TeV. We also have triggers that I won't go into that have other objects in the HLT like BJS and missing ET, with slightly lower VBF threshold. And you can see already one example in the archive of how you might want to use this trigger. So I'll switch and talk about missing transverse momentum or missing ET now. I'll mention the motivation, talk about how we handle pileup at level 1, which is really crucial. And then the same question in the HLT using new algorithms and show the performance. The missing transverse momentum, or missing ET, is a way that we look for invisible particles. So for example, if you have this event display, you can see that on one side of the event, there's a very high PT jet, and on the other side of the event, there's nothing. That tells you by conservation of momentum in this plane that there has to be another particle. And so this is how we look for invisible particles, such as dark matter. Now, most of our events are not this extreme. This would be, I think, a very easy event to identify. So usually we're looking at much lower thresholds, things that are look a lot more like the background. And so it turns out this is very susceptible to pileup, and so we need ways to deal with that at level 1 and the high level trigger separately, and I'll start with level 1. So after the filtering techniques that I mentioned, one of the last handles is just the ET threshold on individual towers. So if you imagine looking at the sketch on the left-hand side, you can see that there might be a few high ET towers that stand out, and then a lot of noise towers that are just not very energetic from pileup. So we apply a threshold and we cut those out. It's at about 1 GeV. And then you take the remaining towers to compute the missing ET. And then the calculation is just ET times the cosine of phi to get the EX, and similar for EY. And then we take the magnitude of the two to get the ET list. And the impact on the rate is really substantial of this cleaning. You can see, for example, just these few runs where we made this improvement and reduced the rate from the black to the blue and the red. So this is a significant way we can clean up the missing ET rate at level 1. The next question is about the efficiency, of course, because you need to also understand what happens to the efficiency when you do this kind of cleaning. So the way we measure the efficiency is by using Z to mu events, where the muon PT is a proxy for the missing ET, because muons are essentially invisible to the calorimeter, at least the liquid argon. And the deposits they do have are essentially negligible for this PT scale. And you can see the backup for why that is. The plot on the left shows the efficiency as a function of PT mu. So if you integrate to the right, then of 150 GeV, then you can see the plot on the right, which shows the integral efficiency, which is about 95% efficient above 150. Then it's also split up into efficiency for the entire year, and then the 3 periods on the last slide, where you can see that within about 2% shifts, the efficiency is stable within all of these level 1 settings. And so given the change in rate, this is really a significant statement, because it shows that we're able to control the rate and also accept all of the interesting events as well. So switching to the software trigger or the high level trigger, here we have different inputs. We have the entire calorimeter, and we have a much longer latency where we can use up to about 150 milliseconds of software. So we have a few different algorithms, and I'll discuss the performance of these. One is very much like the level 1 algorithm, where it just uses all the calorimeter cells with a threshold applied to each cell. But instead of having trigger towers as input, it uses the full granularity of the detector. We compute topological clusters in software, which use nearby cells to group them into clusters. We use jets. And then we have a dedicated pileup subtraction algorithm that we published in this paper that explains, or that removes the impact of pileup. So this shows the comparison of algorithms. So I'll explain what this plot shows. We have already accepted these events at level 1, and then this shows just for the high level trigger what the acceptance is for background events on one axis, and on the x-axis it shows the efficiency given a PT of the dimuon system of 175 GeV, which is actually a little bit tighter than what we typically want to do, but it illustrates what a way to compare the algorithm. So the left-hand side is for mu less than 20, and you can see that the ordering of the algorithms is PU fit is better than TCLCW, which is cluster, and then MHC, which is jets, which is better than cell. And bottom right-hand corner is the best of all the algorithms. But then once you switch to higher pileup, then the order actually flips, and you see a really significant gain of pileup fit compared to the other simple cluster-based algorithms. And the CellNet algorithm is actually doing a much better job of maintaining performance at high pileup than the simpler cluster algorithm. This plot is a snapshot summary showing all of the different triggers we ran in the HLT during the 4 years of run 2. And you can see from left to right the evolution of the rate. So the rate is decreasing, and we introduced a new algorithm. And that's the most striking changes between the orange squares in 2016 and the purple triangles in 2017, where we introduced the PU6 algorithm. Then we also did some additional tuning where we utilized the CellMed algorithm because it does actually have relatively good performance at high pileup. And so we can use that to reduce the rate by another 30 or 40%. Slide 19 shows the efficiency as a function of PT mu mu, and then the inset shows the efficiency as a function of mu. And you can see the efficiency for each of the years using the triggers that we ended up using. And for the most part, they're very stable, with the exception of 2000, or very similar and stable. But the one exception is that 2015 is a little bit better efficiency than the other years, about 5% better, above 150 GeV. And that has to do mostly with the fact that we had very low pileup in 2015. So in summary, I described the Atlas trigger system to you and pointed out key features for dark matter triggers, particularly jets and missing ET. I described the jet triggers and some improvements for jet triggers, and then missing ET triggers and how we dealt with the impact of pileup and how we reduced the rates and maintained the efficiency as much as possible. I link here some papers for further reference if you're interested. And if you have specific questions, let me know. After the session, I can join the Zoom room here, which I created, but do let me know if you would like to do that. Thank you.
Thank you very much. Questions? Okay, so you mentioned that these hadronic signatures are especially important for the dark matter and these things beyond standard model, which will be definitely the main topic, for example, for the high luminosity LHC also. So first thing, you are using for this just the colorimeters, or you are using also other parts of the detectors?
So for the triggers that I discussed here, the level 1 only uses the colorimeters. And then in the high level trigger, the missing ET only uses the colorimeter. And the jets almost exclusively use the colorimeter except for one thing, where we have very high PT jets where we've computed the tracks already for B jets. And then we do use the tracks to improve the calibration of high PT jets.
Okay, yes?
You were asking about high luminosity as well, or?
Yeah. Now the second question is exactly about the high luminosity, and if you will be able to more implement, for example, in a tracker to these analyses.
Yeah. So the plan for the high luminosity LHC is to instrument the entire liquid argon for the first level trigger, which is called level 0. So you get all of these cells, and then run something called clustering, which kind of groups those together. That happens in the first level, so you see the 40 megahertz input rate. And then the inter-detector tracking, it's possible that that will be available at a reduced rate of either 1 or 4 megahertz. But that's not in the first level trigger, it's kind of a split level trigger. So in that case, it would be a 3-level trigger, and then the level 1 information, then we will call it level 1, and you have tracks after either 1 or 4 megahertz.
Okay.
Yeah. Does that answer your question?
Yeah, perfect, thanks. Other questions? If not, thank you very much again. And we are going to the last presentation of today's session, which is Mark, and we will stay with Atlas and multi-3-aided operation for triggering.
All right, can you hear me?
Yes.
Okay, I should be sharing screen now.
Yes, we can see slides.
Okay, so I'm going to talk to you about preparing the Atlas trigger software for multi-threaded operation. So as Kate and Ben have already been talking about in the session, it's the Atlas data flow. So you see the Atlas detectors and the data flow that then comes from these through the level 1 system and then into the high level trigger. And then this interacts with the data acquisition system, which of course then also writes this out to the permanent storage at CERN. The HLT farm during run 2 consisted of 40,000 processor units and had a peak input rate of 100 kilohertz. This produced an output rate of 1 kilohertz on average per LHC fill. This talk I'll cover really the software that's running on the HLT, and this is based on the Athena software framework, which is also what we use in Atlas for reconstruction, simulation, and physics analysis too. So why are we talking about multi-threading? Well, the CPU to run Atlas reconstruction will really increase dramatically when we get to run 4 and beyond. And so in this period, given the expected modeling of the CPU budget and the R&D that we're planning to do, that if we don't do changes, then we would really not fit within this budget in the future. So we really are trying to start the improvements now, even though in run 3, we should really easily be able to take the data we have with the existing software. Why are we then for multi-threaded? Well, the single thread performance has really plateaued in the computing market, and yet the number of cores is still growing. However, memory is also not getting cheaper, which means then that the maximal throughput for your processing is really limited by the memory per process. Additionally, if we move to multi-threading, the software could then make use of accelerators. So for example, we could use a GPU to process a thread entirely. So in run 1 and 2, we were using Athena, which was based on Gaudi, which was not designed for multi-threading. So what we're now designing and implementing is Athena MT. This has the HLT requirements really included from the start. So this includes partial event data processing. It includes 3 different types of MT processing. So you have inter-event, which means that multiple events are processed in parallel. You have intra-event, where multiple algorithms can run in parallel for an event. And then you also have in-algorithm, where algorithms can utilize multi-threading and vectorization. So you can see in the diagram just an example where you have 4 threads, and you can see that you have an event being processed in 2, while you're also having 2 extra events being processed. And these are really, the first 2 are really the aspects we're looking at using at the moment within Atlas of this multi-threaded processing. This processing of an event is really managed by every algorithm that we're trying to run, having an input and output data dependency. Once the inputs are available for an algorithm, then the Gaudi Hive scheduler pushes this into the Intel thread building spot queue. The execution is then also depending on how many number of threads and event slots we have configured. So the way we actually are running this in the HLT itself, we have the HLT mother process, where we have 1 of these per processor unit in the HLT. This process is what loads the whole configuration. We're using Athena in the past, now Athena MT. And then from this, we then fork child processors. So the mother really is just handling these child processors. It doesn't handle actually any events itself. And this is really the same multi-process approach that we were using in run 2. The memory was then saved in run 2 because we were then really only using copy on write. So we were loading as much as memory at the start, and this would then change very little during a run. Each child then runs a single instance of Athena to process events sequentially. And then each child, the HLT child process itself is what was driving the event loop. So this was requesting events from the data flow and then sending them to Athena to get processed. In run 3, this is slightly different. So now we can, because we're using multi-threading, we can really share both read and write memory. The Athena MT on the HLT child process now also can contain multiple threads itself and also multiple event slots. So within here you have multiple threads, and here each of these then has extra slots. Athena MT now actually does the requesting of the events, where it passes this request through the child process, and it does this when it has 3 processing slots available. So really the interfaces that are processing using it have also been changed, as well as the setup of the Athena MT. The offline emulation of this configuration is really improved, so we have better development and testing where we can really replicate this offline rather than having to run this on the HLT farm itself. The performance will be really optimized by really adjusting the number of forks, threads, and slots. However, it's not just an optimization we have to do for performance. We also have to account for stability. So if there is a crash in Athena, or if the process reaches a processing timeout threshold, the event data is what we call force accepted to a debug stream for offline and debugging or recovery. So this means that the whole event just gets passed without any HLT processing inside of it. In run 2, in this case, a single event that was being processed by Athena would get written to the debug stream. In run 3, this now applies to all the events that are being processed in the same fork at that time. So this means if you have too many event slots per fork, this increases the number of unrelated and potentially good for physics events in the debug stream. However, the number of threads really does not affect the number of events lost. So these events could still be recovered, but it means we have to do more offline processing to really look at these events. So for the software itself, well, what we actually run on the HLT is an event selection based on what we call chains. These are built up of different HLT algorithms which share as much code as possible with the offline versions. And then they have hypothesis tests to test conditions for acceptance of these chains. The chains are seeded by level 1 items, and in run 2, we had roughly 1,500 of these active. The HOT takes on average around half a second to process an event, which compares to 30 seconds for offline reconstruction. So to have these two running very similar code, we have to achieve this by the HOT only reconstructing part of the event, which is what we call regions of interest. So these are defined as cones around the collision point, around the interesting objects in the event, and then these HOT seeds are then provided by the level 1 trigger. We also implement early rejection, which actually you heard earlier in the LXCB talk, where you're trying to really process only part of the chains, and you have the early parts are fast, and then later on you do the more complicated detailed analysis, and so you only do these where necessary. In run 2, these features were really achieved by custom HOT scheduling and data caching. For run 3, the HOT software is rewritten and integrated into AthenaMT. And this is not just a rewrite of the aspects related to multi-threading, it's really a rewrite of actually nearly all of our HOT software. This is really allowing us better unification with the offline software and also the framework itself. And then the really specific HOT extensions that we have on top of this is the event views, which is what provides a part of the event reconstruction. So this is just serving up only part of an event rather than the whole. And then the control flow, which we use for early rejection, which I'll go through next. So to process an event, we have, as I talked about earlier, we're input and output data dependencies. So you can see as each of these dotted lines go through all of the algorithms, these are individual chains, and then the black lines represent a data dependency to go through one of these steps. To begin with, each of the chains are built up of 4 algorithms. So we have filter algorithms, which are really running just to make sure the inputs are available to the algorithms. Then we have the input maker, which really goes and takes the information from the specific region of interest that you want to process. Then you have a reconstruction algorithm, which then processes the data in this and extracts the features you want. And then finally, we apply a hypothesis on this, where we really then check if the data we've reconstructed passes what we want to accept. This whole control graph is created in initialization, and the events are, the steps are then exercised based on what data is available in a particular event. So as the filter passes, we keep going through into each of the subsequent steps. But should we fail, then we stop processing. So then all of these subsequent steps would not get processed. And this is how we then save CPU online. If we reach the last step with the chain still passing all of its steps, then this is when we accept an event. All of this configuration is actually stored initially in the trigger database, and it's loaded as part of the HOT initialization. So in run 2, this database structure was represented by a table per object. So we had something like 90 tables, which were all filled by parsing XML files. This information was then accessed by 4 what we call keys, which are the primary keys of all the relevant parent tables in the database. And if you want to learn more, there's a new paper that's just been published this week onto arXiv. In run 3, this structure becomes much simpler, as most of the database schema will now be replaced by directly storing JSON files. So this means that these files now contain the objects that were holding all of these subsequent separate table informations. So it means our schema is now much more simpler because we have only 10 tables, and so all of the interaction is faster. This is easier to extend during data taking rather than trying to update a database schema while we're taking data. And then also, it does have the downside of having increased data duplication, because these JSON files, the whole point of the previous schema was to reduce as much possible the data duplication, use links to save on this. But this created really time-consuming lookups for saving information when we got to the end of run 2. So this was really deemed much more important to save. So this is how the process we go through now. We also, by doing all of this, is removing an extra step of converting the data. So no longer do we go from XML into a database and then into some metadata storage for offline processing. We now directly store these JSON files also into the offline data. So this means that when we're accessing data without database access, we're really parsing the same information. So it also saves us on the software that this unifies how we read all of this in several places too. So as a summary, AthenaMT is being developed to prepare for future data taking requirements and the available computing resources. The core functionalities to be able to run the HOT are in place, and the full set of algorithms to deploy the run 3 menu are really being developed. The validation campaigns are ongoing, both offline and online. So this means using Monte Carlo data replaying run through data through the actual HOT system, or also actually now taking live cosmic and random triggers with the updated software. The performance studies have started, but really the final configuration of this MT usage will be measured at the start of run 3. And if you want to find out some more information, there are also 2 other related presentations at this conference. Thank you for listening.
Thank you very much. Very nice presentation. Questions? Okay, I would have a question actually. So you mentioned already run 2. So you were already trying the first steps on run 2, or?
No, no. Well, the parts we were doing in run 2 were this forking process. So even though Athena wasn't multi-threaded, we were able to use it in multi-process. So this was what saved us the memory in run 2. So we just now have much more flexibility in run 3 that we can also run multi-threaded as well.
So do you have any expectation how it will change the throughput or the speed, or is there some ratio of how it was before and what it should be, for example, for run 3?
So I think online, we will really gain by really more the effect that we're rewriting the software to be closer to offline. So we will gain that we will have the same workflows and the same much closer selections. Actually, processing-wise, the throughput will be very similar to between run 2 and run 3. The performance gains for actually using the memory more efficient are ready for the offline processing. We just benefit by being more in sync with how offline processes events.
I would expect that this is also the future for run 4, or is there some different plan? Or?
Exactly. So this is really the starting point where we can, if we develop this now, then we can expand on this for run 4, and we can really see how to really improve our performance to know what our limitations are, because certainly this will be different. And so then we would be looking into running this on GPUs, for example.
Okay. And last question, you mentioned, of course, that Athena is not used only for triggering, but also for data analysis and Monte Carlo simulations and these things. Is this multi-threading or this parallelization also usable, or will it somehow affect also these let's say aspects of Athena?
Exactly. So all of that, the software is moving to Athena MT. So yes, everything for the reconstruction simulation will all move to this as well in the future. So it's really a rewrite of all of our software to be ready for the future.
Okay, and the future for this, let's say, analysis or simulations is also run 3 already?
That's right. Yeah, it should be for run 3. Yeah.
Okay, perfect. Okay, thank you very much. Are there any other questions or comments?
Yes, maybe. So I guess many of your algorithms access common things like geometry, or did you have to kind of rewrite how algorithms are using these things?
We didn't have to rewrite so much how but we do have a different system in the core framework. So yes, it is different to how we were doing it in run 2, but it's I mean, these were the first things that were developed, was to make sure that the core framework is there in place so that you can access this information, especially when you're running multiple threads accessing the same information. For the developer of algorithms, these are actually quite small updates that they have to do. This is really handled by the development of the framework itself.
But so, for example, the geometry is still kind of accessible from any place?
Yeah.
Okay, any other question? Okay, if not, thank you very much again. Thank you for this presentation, and thank you to all the speakers of this very long session. I think it was, we had a very dense but beautiful program. Thank you very much for preparation, such a nice presentations. I think that we can now close the official program. We can close probably the recording and live stream, because we are already significantly late. But of course, if there would be some discussion following, the room still